So thank you very much, and I would invite the first invited speaker to begin. And the first speaker is Mr. Panos Panagos from CERESiS. So, Mr. Panago, the floor is yours.
Good morning, everybody. I'm not so used with the, this application, but we'll try to, okay, I think now it's shared, I think it's shared. You see it, okay. Good morning, everybody. My name is Panos Panagos. It's my pleasure to be here. Okay, as you may understand, it's quite difficult for us to understand to be present in different projects presentations. So I also try to do my best to be here, and I will be as much as possible because at 9:30 I should connect with China, where we have a global soil erosion assessment, and with FAO, and we have to assess global soil erosion. So I will present briefly what is the role of the EU Soil Observatory supporting policies, and I hope that my presentation will not be out of the box, will somehow give you some important insights on what we are doing here in the European Commission, the Joint Research Center, in relation to soil, to the policies related to soils. So I'm working in the European Commission, the Joint Research Center, and okay, the general contents in general about what we are doing and why we do this work on soils, why soil degradation is important. It's important because according to our last assessments, 60 to 70% of soils in the EU are not here. 24% of land has unsustainable water erosion rates. 78% of land takes place close to agricultural land. All the costs of land degradation may be around 50 billion euros according to the last impact assessment of the soil monitoring law. We lose around 7.5 million tons of CO2, and 25% of land in Southern and Central Europe is a high risk of desertification. And in the context of your meeting today, we have identified 300,000 contaminated sites in the EU. It is estimated that the number of contaminated sites is 2.8 million, so we'll speak about a huge number of contaminated sites. It's an important activity that we do on this topic. And finally, 65 to 75% of agricultural soils is in high nutrient, suffers from high nutrient inputs. So the European Commission till 2020 has somehow neglected the important role of soils. I'm working here for more than 22 years, and I have seen different phases, and unfortunately soils was not high in the agenda. But in 2020, the picture completely changed. It completely changed with the EU Green Deal, where soil is featured among the 5 objectives of the EU Green Deal. To increase the EU climate ambition for 2030-2050, we know that soil is a carbon pool. To mobilize industry for a clean and circular economy, the importance of soils in circular economy. A zero pollution ambition for a toxic environment, soil contamination is an important action. Preserve and restore ecosystems and biodiversity. So the soil biodiversity is as equal as the above ground biodiversity. And of course, from farm to fork, the nutrient excess and fertilizer and the use of pesticides is an important action. So soil is a cross-cutting issue within the EU Green Deal. And in 2021, the European Commission proposed the EU soil strategy, where you can see that soil is somehow a cross-cutting among different policies like the Zero Pollution Action Plan, the circular economy, the chemical strategy, the biodiversity strategy, the Fit for 55 package, climate adaptation, farm to fork, and many other policies. But the major change came last July. In 5 of July, when the European Commission for the first time proposed the soil monitoring law, an EU legislation which provides a harmonized definition of soil health, puts in place a comprehensive and coherent monitoring framework, and wants to focus mostly on soil management and the remediation of contaminated sites. So it's important, the issue of contaminated sites. And here you can see 7 blocks of the soil monitoring law, the definition of objectives, the definition of different criteria about soil health, monitoring and assessment, how we do monitoring, services and support, sustainable soil management, contaminated sites, and at the end, the reporting. Where we are on this proposal right now. On 10th of April, the proposal has been voted by the European Parliament, the European Parliament has given a positive opinion, and now, in 17th of June, we expect the Council will give also a positive opinion, and then the three bodies, I mean the European Commission where I work, the European Parliament, and the Council will come with a common, with some changes in the proposal and the common text. So in this context, the European Commission in 2021 established the European Soil Observatory. And the European Soil Observatory has as a main objective to provide knowledge for soil policy at European scale, and has 5 objectives: to have a harmonized wide soil monitoring system for the EU, to monitor the impact of different policies in soil health, to have a strong European soil data center. Of course, we're a research organization here and we want to continue to do research and innovation. And finally, to participate with different stakeholders and to create a forum, or the famous EUSO stakeholder forum, where we interact with different stakeholders. So briefly, I will explain each of the 5 objectives. So the GRC here manages the biggest survey ever done in Europe, the biggest harmonized survey, which is named Lucas. So practically, we have to make the design of the survey, the selection of points, the training of surveyors, the protocols, the analysis which will be done with a laboratory that we select, finally the quality assessment, and then when we receive all those data about the points, we have to do with artificial intelligence and advanced modeling techniques, maps that you can see on the right. So practically, we manage 4 surveys, 4 soil surveys, 4 Lucas surveys, 2009, 2015, 2018, and 2022. All those data are available, except the 22, which now are analyzed. In 2022, in general, Lucas is analyzing 20,000 samples in the whole of Europe. In 2022, we have increased the number of samples to 42,000, and we have a big archive here in GRC. And our next objective is also to work closely with member states, with countries where there are many data coming from different surveys. So practically, what we do from the field to the laboratory, then different soil properties like soil organic carbon, nitrogen, phosphorus, heavy metals, pesticides, fungicides, antibiotics, soil biodiversity. We analyze those properties, and not only this, but it's a huge amount of properties. And with modeling and artificial intelligence, we create those maps, which at the end have to support different policies, like the EU Strategy 2030, the soil mission, the carbon farming, the nature restoration law, the zero pollution action plan, common agricultural policy, and all those policies that I showed very briefly in the first presentation. An example of what we do with the Lucas. I take the attribute or the parameter which is of huge importance, which is the soil organic carbon. And we see that between the 2 surveys, 2009 and 2018, with measured data, we estimated that we lose around 0.75% of soil organic carbon, which is translated around 70 million tons in the first 20 centimeters. Of course, there might be, you can see a huge variability because different places in Europe may lose or may gain carbon. But mostly the important stuff is that we lose in general carbon of the EU, and this is mainly due to some conversion of cropland to grassland to cropland, and also due to climate change. So we lose carbon with a small rate, but the conclusion is that we are losing carbon. The second objective of the Soil Observatory has to do with the European Soil Data Center. When we store our data sets, we make them available. You may have visited this, you may have downloaded some data, and it's an open portal where people can, any kind of colleague can download our data sets. And we speak about 120 blocks of data, 300,000 visitors per year, more than 80,000 total data downloads. It's one of the most visited websites here in the GRC. And in addition to this, we provide a knowledge platform with atlases, with maps, where people can be informed about different, we contribute also to awareness raising with those maps. So somehow after 2024, we want to this European Soil Data Center to be advanced with taking data not only by house developments, but also data coming from countries, data from the soil mission, and also we want to have an enhanced functionality. The third objective has to do with the assessing the soil health. So recently we have published the EU Soil Health Dashboard. The EU Soil Health Dashboard is showing that 63% of EU soils are not in healthy situation, which means, okay, it's not, somebody can receive it as a dramatic message. It's not so dramatic because unhealthy does not mean that the soils are completely not productive. It means that it's like a person. You may have a headache or you may have a cancer, but unhealthy means that you may have an issue and you have to treat this issue. So this dashboard is based on 18 indicators that we have published, and this dashboard shows as well the location of different types of soil degradation. And this dashboard as well has different functionalities, like the dependency wheel showing different processes how depend each other, the number of concurrent processes, and also shows area where you have certain issues. So this dashboard is based on, as I said, 18 indicators, and you can see here the main blocks like soil erosion, and then soil erosion we take into account water erosion, wind erosion, tillage erosion, salinization, soil compaction, loss of organic carbon, loss of peatlands, degradation of peatlands, soil nutrients, of course, so excess of phosphorus or phosphorus deficiency or nitrogen surplus, loss of soil biodiversity, important issue about soil pollution, where we have issues with copper, mercury, zinc, and cadmium, and finally the soil sealing. So besides our contribution to the soil monitoring law that we as GRC have provided much input in the impact assessment in the proposal for the soil monitoring law, we work closely with other policies like the soil mission, the nature restoration law, the development of clean soil outlook, the carbon removal certification, which is a new legislation that's very important for farming, the review of CAP and the performance indicators, which are the soil organic carbon and the soil erosion, and of course the farm to fork, which we somehow estimate the impact of pesticides and nutrient indicators. So I go to the fourth objective, which has to do with research and innovation. We are a research organization as well as GRC, and we have a small group of 10 people. So every year we do quite a significant amount of publication. 45 publications last year was quite huge, quite high number. So we could host also some PhD candidates, and important that we contribute to the implementation of soil mission. The soil mission is an horizon project, but the soil mission is part of the horizon, but in a different way. I mean, the Commission has proposed 5 aspirational targets, and soil is among the 5 aspirational targets. And with this soil mission, we want to make a radical change in soil research in Europe. And we work closely with many soil mission projects which already started, like I4Soil Health Benchmarks, and EOSO, the EU Soil Observatory, is considered as a beneficiary of the research activities of the soil mission projects, but not only of the soil mission projects, but also other horizon projects at the end. I'll give you a flavor, since your meeting is about soil contamination. Lucas has an important component on soil contamination. So we have analyzed the Lucas for 12 heavy metals, and we have done assessments of most important of them, like copper. So we have assessed the 22,000 Lucas samples for copper. We have seen where copper excess takes place, and very important, we want to understand how copper concentration is correlated with physical attributes, but not only this, to see also the anthropogenic part. The anthropogenic part has to do with, for example, vinegars. Vinegars have the highest mean copper concentration in Europe, and olive groves as well in Greece, and different orchards because of frequent fungicide assessments. So practically, we have seen the highest copper concentration in north of Italy, because where we have a lot of vinegars and wet areas, the farmers continue to do frequent fungicide treatments. And as I said before, we try to see also different anthropogenic sources of copper inputs, like fungicide treatments, liquid manure, sewage sludge, atmospheric deposition, mining activities, local industries, and at the end also particles from car brakes. The sewage sludge has also an important contribution, because almost 10 million of tons of sewage sludge is treated annually, and 40% of this has high copper input, and particularly the pigs and liquid manure in the EU is, I mean, the 150 million pigs consume more than 6.2 million tons of copper. We have all these kind of published in different papers. I go to the second heavy metal that we analyze, which has to do with mercury, which is a toxic element. And this has, together with lead and arsenic, are three toxic elements with important impact in human health. And we know the case of Minamata in 50s. In general, the EU, we have low level of mercury, except 0.8%, where we found that mercury was higher than the threshold of 0.5 milligram per kilogram. And the mercury is mainly influenced by high soil organic carbon, temperature, and DVI and land carbon. The mercury pool is estimated around to 45 million tons. And we try to understand where those hotspots of mercury are mainly close to anthropogenic activities of past mining activities like Almaden district in Spain, Asturias, Idrisa mercury mine in Slovenia, Monte Minamata in Tuscany, and iron ore mine in Slovakia. But also high concentration of mercury are found close to coal power plants, chloralkali industries, old chloralkali industries, and some local diffuse contamination due to small industries which are employing mercury for electrical equipment, dental amalgams, and disinfectants. Finally, I will speak about the recent research that we have done on cadmium. So cadmium inputs to topsoils have increased significantly during the 20th century because with fertilizers and certain fertilizers coming from Sahel region in Africa have high cadmium content. 70% of the samples have very low concentration, below this very low concentration, 0.07 milligram per kilogram. But a high number of samples, more than 5.5%, have high value, higher values, more than 1 milligram per kilogram. And again, we try to understand the physical drivers like pH, soil organic carbon content, but also the anthropogenic one. So in certain areas where input of phosphate fertilizer had high carbon input, like we have seen this in Poland, in certain parts of Ireland, we have found higher cadmium content. So finally, going to the, I would like to underline that in our group, we do quite important research on different topics like soil organic carbon, like soil erosion. You can see the assessments in the middle. I'm responsible for this part, and also on various nutrients. So those assessments have quite important impact also at research, but also at policy level in the EU. So I jump to another topic which has to do with the Horizon Europe and the soil mission, which I briefly mentioned before. So the soil mission has 5 building blocks: research and innovation, to establish 100 living labs, a harmonized soil monitoring scheme, which the GRC, the EU Soil Observatory, is responsible, and finally the soil literacy and communication and citizen engagement. So the soil mission for the next 7 years, from 2022 to 2029, is an important funding mechanism for research projects in the EU. And if you want to see how the puzzle of soil protection in the EU is somehow shaped, you can see in this slide. For policies, you have the EU soil strategy and the soil monitoring law that's proposed. The GRC and the EU Soil Observatory manage the knowledge, provide support to policy, and is responsible for soil monitoring data and legacy. And finally, we have the missions, which is the mechanism for research and innovation. I mean, it's the funding body, which at the end provides funds to do further research on soils for citizen knowledge, to cover certain knowledge gaps and citizen engagement and wide outreach. Here in this slide, I try to show somehow how the involvement of EUSO starting from 2012 till 2030. From 2012 till 2021, we have followed the top-down mapping, which means that we have done in-house assessments at large scale, and we have developed the EU soil health dashboard that I showed before. Now the soil mission is launched. Many projects are replaced, and with those projects, plus we speak about 100 projects, and with another 100 living labs that will be in place, we are going to reverse somehow the trend and to have a bottom-up mapping, to have the knowledge coming from bottom, And with this huge investment of €1 billion that comes from the soil emission, we expect that by 2030 we'll have better assessments of soil health in the EU. So finally, about soil, about the fifth objective of the EOSO, which has to do with awareness raising, we do also, as well quite a lot of activities in supporting citizen engagement and awareness raising, like many atlases, like the Soil Atlas of Asia recently published. We participate in conferences. We also promote the Soil Mission Manifesto. It's an important activity I call you to sign if you want to be friends of the Soil Mission. Of course, we do the stakeholder forum and we involve the young scientists, and we also participate in course. We have developed citizen science databases in summer schools, etc., etc. Finally, an activity which is important and has to do with interaction with stakeholders is the EU Soil Observatory Stakeholder Forum. This takes place around September, October. The last three editions, we had more than 1,000 participants online, 21, 22, and 23 were the three editions. With high-level participation, you can imagine in the 3 days we have 70 plus presentations. In the last forum, we had also presentation of the first soil emission projects. And then after the online stakeholder forum, we moved to a physical meeting, which is the Soil Emission Week. This was done in November in Madrid. And we also have established how we work. We have established 6 working groups on pollution, on monitoring, on carbon monitoring, reporting verification, on data sharing, on soil erosion and soil biodiversity. So those working groups are places where we interact with experts. And at the end of each year, we also publish our annual bulletin, which summarizes the activities of the EU Soil Observatory. So I expect there are many young scientists there, and also we support the young researchers who, in one of the activities of the forum, was to give place to young scientists to express their research. And we, in the first forum, we have selected 4 themes, and the young scientists have come with new innovative presentations, and we have discussed this. We have published this in nice journals, and it was a nice interaction. Finally, we also work beyond the EU, so we work also globally. A recent example is the Soil Atlas of Asia, but also assessments at global scale on soil erosion. I told you that now I'm going to move to the FAO presentation in a few minutes in order to participate in this forum and to present the global assessments that we do at soil erosion. What is next in our work is to do, now in 2024, we do an assessment, a report of what is the status of soil health in Europe. And this is important for assessing every 5 years to see the progress, but also to contribute to the FAO State of World Soil Resources. We go towards a new Lucas design. So I have explained briefly what is Lucas, but now we go to more advanced Lucas. We update the soil health dashboard with new assessments in order to monitor the soil monitoring law. We do advanced assessments in soil biodiversity and antimicrobial resistant assessments. On soil biodiversity and pesticides, we work quite a lot. We work also in soil fertility, land degradation desertification methodology. This is an important activity because the EU has to declare itself as a party affected by desertification. And of course, we want to develop soil organic carbon-based lines and to provide some innovative soil health assessments. Thank you very much for your attention. I hope I gave somehow an interesting overview of the activities that we do.
Thank you, Panos, very much for your very nice and interesting presentation. I think that it was very relevant to the work that we are doing, especially with regards to the datasets that you collect, mapping the lands around Europe. I think this is something that I would dare to say that maybe CERESiS share the common vision with the DSS, trying to collect the information so as to be able to have the tool to support policy decisions. So considering that you have to go to the next meeting, I think that maybe it's a good opportunity to have some questions from the audience to you, if there is anything that people would like to ask before losing you afterwards in the discussion. So is there any questions from Thanos? So Thanos has a question.
Thank you, Panos, for the extremely interesting presentation. A quick question from me, because we are one of the challenges we had in developing the decision support system was the lack of data to feed this system. So my question is regarding the soil data that you have collected and processed. Are these available, the raw data, the databases? I know there are maps, and we've seen the maps, a lot of maps with contaminated. The underlying data, is it available?
Yes, very interesting and hot question. I mean, all the Lucas data are available. All the Lucas texture, soil organic carbon. So the 3 Lucas are available. The only restriction that we have is with heavy metals. We have a restriction with heavy metals because we speak about sensitive data. Sensitive data means if we have found some high values, I said before, like 1% of certain sums, we speak about 1% means around, can be 200 sums or 400 sums for 2%. In the case of cadmium, more than 1,000 sums have been with high values. By showing with exact coordinates those values, we go against privacy issues. So a certain piece of land can be considered very degraded, and then when we have issues, you know, there is the privacy. Many farmers may go against us. On the other side, there is the transparency. So you see sometimes that the policies also in the EU are conflicting with each other. I'm in favor of openness of those data. That's why we have done all those assessments of maps. So practically, if you download the copper map or the cadmium map, wherever you will have high values, of course, means that around there are values which are high, because those have been developed with high advanced machine learning techniques with models very advanced. I can confirm that we have done quite a high advanced work on this. But unfortunately, the point data on heavy metals are not available due to this privacy issue. But in general, my view is that we are as much as open. And my big, let's say, bet now is that from all those oil mission projects, we'll have a catalog with all the data that the projects will make available. So in the past, I'm working for 20 years here. In the past, projects have produced nice results, have developed databases, but all this somehow have been lost somewhere. Now, our objective is to recuperate, but also in your projects, if you have developed important data, I will advise that we have a kind of collaboration and we can upload those data sets in a portal that we are currently designing. Thank you.
Thank you, Panos.
Thank you, Panos. Any other question maybe from the audience? Well, if not, then Panos, thank you again.
I will stay for the second presentation. We'll try to be for the biofuels because it's an interesting topic, and then I will escape. Thank you.
Okay, great. Thank you, Panos. Okay, so now we've heard about the soil part, that is the first, let's say, consistent of the CERESiS project. And our next invited speaker, Mr. Nikos Liapis, he's an energy and business and fuels consultant. So he has an experience of maybe more than 30 years in the field of technologies and fuels and also biofuels. So he will be talking to us about biofuels and technologies. So let's see how we can blend both aspects of services together and see where we go. The presentation should be the two, it should be here. Yes. All of the screen.
Thank you very much, Gerbo. Good morning, ladies and gentlemen. Thank you very much for inviting me on that topic, a little bit different from the soil and phytoremediation. But of course, it's the other end of the supply chain and what we want to do, converting conventional fuels and conventional energy into biofuels and in general renewable fuels in order to proceed with decarbonization. So my name is Nikos Liapis. As said, I was working for now 30 years in the oil industry and shipping industry as well. But also I dealt a lot in the past with biofuels. So let me make a quick, let's say, overview of where are we now with biofuels and renewable fuels for transportation and where we are heading for. So I would say that we have, when we talk about now renewable fuels for transportation, we have two parts of that, two categories. One is the classic one that we know, the biofuels, which are from biological origin. We'll talk about them later on in detail about that, mainly biodiesel and used cooking oil, bioethanol, and the new renewable diesel grades, the paraffinic diesels, BTL and HVO. But now we are heading, because of the limitations in sustainability and feedstock of biofuels, we're heading also to deal with the decarbonization of transportation through renewable fuels of non-biological origin, which mainly is at the moment the plastic pyrolysis oil and tire pyrolysis oil, but we go further on for when we have the availability of green electricity to synthetic fuels, as we call them e-fuels, mainly e-methanol for transportation, of course. So until now, we talked about the first generation biofuels, or now we're in a stage that we call them conventional biofuels, that are being produced from agricultural coals, mainly like grain, starch, vegetable oil, and sometimes food waste. So the main categories is the fatty acid methyl esters, biodiesel in general. We used to have some small quantities, but not in a large scale of fatty acid ethyl esters. Of course, biomethanol, bioethanol, bio-LNG as we call it, and bioethers, something that, for example, bio-ETB that we already use in blending with gasoline. We have some, of course, advantages with first generation biofuels. Mainly the technology is mature. We have a relatively low production cost, and I mean by that they're not cheaper than conventional mineral fuels, but they are in a reasonable cost, let's say. We have also a relative feedstock availability at the moment, and of course we have a global capacity that's adequate for this feedstock. But the problem is that we consider them as competitors with the food chain, and we know that we have a big food problem as population first is rising. We don't have the sustainability levels that we would like to, and of course we have technical challenges in some of them. So we move ahead to the second generation biofuels, or advanced biofuels as we call them now, that the main thing is the production process is different, and also we try to have a diversification in the feedstock, mainly coming from residual forestry, agriculture, or urban waste. And sometimes we use also fresh oil because of the availability, and waste oil like used cooking oils. And these technologies mainly is biomass to liquid, technologies that we referred before as well in the CERESiS. I know that you used them. The hydrotreated or hydrogenated vegetable oil, HVO, and bioethanol, but produced with from lignocellulosic feedstock, something that unfortunately it's not feasible in economic way. We'll see later on about production and that. So we have, of course, advantages there. That's where we move to the second generation. They are drop-in fuels, so they can be used in blend easily with conventional fuels. So can use also the same internal combustion engines, the same supply chain, tanks, tank trucks, etc. So we don't need a further modification in all this, and this means that we have a very low cost in implementing them. They have, of course, specialized chemical production, but this means that we have more stable fuels, like HVO, for example, than the first generation. And they have advantages with the land use change, which is low, and there's no competition with the food sectors for most of them. But we have some disadvantages as well. The process in general is typically more costly than conventional fuels. They have limitations with feedstocks as well, and there is a limited production capacity at the moment. We have seen constructions of plants like this, but we're now in the beginning. Of course, we are already talking about the third generation, which is the future. The technologies are not yet mature. For example, biofuels coming from algae or from microbes, but we're still in an early stage, not even in a pilot stage. So from all these biofuels, we have something that started from conventional biofuel, which is the used cooking oil, methyl esters, but because of the recycled carbon that they use, because they're waste, the feedstock is a waste, we consider them advanced biofuel as well. So it will keep on, this stream, let's say, of biofuel keep on and for the next years as well. But what we see, because of the limitations of sustainability in feedstock in biofuels, that we have a big feedstock and new technologies arising to use renewable fuels of non-biological origin. We use now in the European Union this umbrella term, let's say, for all these gaseous and liquid renewable fuels that they do not rely on biomass. And the main technology for that is to use electrolysis to produce green hydrogen, and then we capture carbon dioxide, so recycled carbon, in order to proceed to synthesis of syngas, and then to have some other streams of gaseous and liquid fuels for that. And also we have another technology which comes to about plastic and tire pyrolysis, which produce an oil that it's similar to hydrocarbons, to conventional hydrocarbons, so it can be used in blends in fuels as well. So because we see a future in that, the European Union has proposed the formula, especially for the maritime fuels, the bunker fuels, to mandate a minimum 2% share of RFNBOs to use in shipping, and also for the land transportation, there is also a minimum percentage that will grow up to 2035 when we consider that we will have, let's say, industrial scale production of e-fuels. I will not stay a lot in biodiesel, in fatty acid methyl esters. It is the most conventional, most used biofuel, along with bioethanol. Is a drop-in fuel. Of course, it has some problems with cold flow properties, with degradation. We'll see it later on. But it has a high certain number, a very good lubricity. Excellent lubricity is something that we need in conventional fuels now that we have low sulfur, which had the mechanism to increase lubricity in fuels, which is something very useful, of course, in internal combustion engines. We have a lot of technical challenges like lower heating value, the increase in NOx emissions for higher blends, and of course, microbial sludge formation, very big problem, and of course, a lot of sustainability limitations. So it means that when we go to higher biodiesel blends, in order to increase sustainability in fuels, we have a lot of challenges. Also due to difference of the behavior in the internal combustion engines, especially due to higher heating value or to higher certain number from the opposite, and of course biofilm and stability. We talked about EUCOME. It has no sustainability issues. In many countries, it is in double counting form. It means that you can have that and count it for twice the blend part. From the sustainability point of view, but we have significant feedstock limitations because there's not big consumption of oil in frying, mainly because that's what we take it back. And so about biodiesel blends, what we see is that the best information now we know that we have in all Europe 7% blend of biodiesel in the normal diesel. Nobody knows about that. Doesn't need to know. It's in the specification, but we consider going up to 20 or 30% of biodiesel in order to increase sustainability. And we can see that with concentration up to 15%, we have improved a certain number of the fuel, which is especially for diesel, it's something that we want to. And also we can have even some, because of the oxygen that is a bigger part on that. In hydrocarbons, we don't have oxygen. It also improves other ignition qualities and combustion qualities of normal diesel. For the production point of view, it's a very common and very, let's say, conventional now production method about transesterification of the triglycerides of fatty acids. and also esterification-free fatty acids that are especially have good cooking oil. So it's a real conventional, let's say, methodology that we can have can be upgraded to bigger plants up to 100,000 tons per year or even more. So it's an easy and very well-known technology for that. And concerning now emissions, there is a problem with higher blends about increasing NOxes because we have an increased content of oxygen in biodiesel. But it's not a problem when we go to blends up to B20. And we have an improvement in particular matter because again of oxygen. And of course, we have when we have sustainable biofuel, we have a lower greenhouse gas emission, and which is maximum 33 grams of carbon dioxide per megajoule. We said again about we talked about the biodiesel technical challenges with the microbial growth, oxidation stability, of course. It's it has problems with its additives sometimes, and it can lead to the generation of rubber sealings and gaskets, etc. And of course, always we have to proceed life cycle analysis from well to tank or to wheel in order to see exactly what is the sustainability of each stream, something that is done now by the European Union. So moving next to BTL, to the new paraffinic renewable biofuels, we have two streams, let's say, two categories, the biomass to liquids and the liquid and the hydrotreated vegetable oils. The final product is more or less the same. It's a drop-in fuel that can be blended in any percentage with conventional diesel, and it is a very stable product. They are very stable products and very well. The behavior is exactly like conventional diesel, so we don't have problems on that. And the main limitation is for BTL mainly to collect the feedstock because it's residual biomass. For HVO, it's that it's dependent mainly on fresh vegetable oil, so it has the same limitation with biodiesel. The good thing about HVO and BTL, the paraffinic diesel, it's a very good for solution for aviation, for producing sustainable aviation fuels. And I think that most of the quantities produced will be directed to this stream, let's say, of transport fuels. So BTL is a synthetic fuel. There are a lot of technologies like fast pyrolysis, optical fast pyrolysis, etc. In general, we would produce it from solid biomass from residual forestry, agriculture, and urban waste. It is let's say, a complicated methodology. Sometimes when we first go to the liquid, to bio oil, it's heavy, has a lot of problems to be burned in a combustion chamber directly. So it needs a lot of upgrading in order to produce a fuel grade quality. And also it's still an expensive, let's say, process. So we don't have a lot of quantities on that. From the other hand, with HVO, it is also another different process of that. We start from fresh oil and we hydrotreat them in order to eliminate the bonds that we have in the oil, and we have a second stage as well in order to produce, let's say, chains of hydrocarbons that are similar to the conventional diesel. So it's also a well-known technology. The problem is that it's more expensive than biodiesel or conventional fuels, of course, and also that it is still a limitation in feedstock and sustainability of the specific feedstock. Now, concerning the emissions from these two paraffinic fuels, they usually have a better behavior, let's say, compared to conventional diesel fuel concerning NOxes and PM10. They are very good quality fuels in a way. And of course, when they have sustainable feedstock, especially for BTL, they have a very, very good greenhouse gas emission coefficient, and this makes them a very sustainable fuel. From the other part, from the gasoline part, we have the bioethanol, also a conventional biofuel. there is the production there goes about separating hemicellulose and lignin from cellulose in order to produce with hydrolysis to take the sugars that we convert later to ethanol and distillate to separate and purify the ethanol. With the ethanol, we use it either in a pure form, in blend with gasoline, or in converting it to bioethers like ETBE or MTBE in the case of biomethanol, in order to increase the octane number of the gasoline and use it as an octane improver. So the biomethanol from the other part is a more complicated process that we don't have a lot of biomethanol available at the moment and requires a series of steps like biomass drying, gasification, biosyngas sweetening, methanol synthesis, and of course purification. So we can produce biomethanol, but really it's a more expensive, more complicated process than bioethanol. That's why we don't have, as we said, big quantities of that. Going now to bio-LNG, as we start to see LNG in transport a lot in Europe, we could say that the first step is to produce biogas, biomethane, but the classic ways of digestive bacteria that will start breaking down the organic components of all the waste that we have. Then we have biogas, and the biogas must be purified. We must clean it up from all other carbon dioxide, for example, other gases that we have, and also humidity, in order to make it a clean methane as we can, and then to proceed to liquefy it and make it bio-LNG, which is exactly the same with LNG, but a different origin of the carbon atom. So this is the more or less, and we think that because LNG was considered a bridge fuel, it means that with bio-LNG we can use exactly the same infrastructure, the same engines, etc. It means that we really can proceed, and we see now that all the companies in Europe that deal now with LNG, they are, let's say, they allocate funds and resources to biogas production plants in order to secure their supply chain with bio-LNG. And going now to RFNBOs, just a few words about plastic pyrolysis oil. It is, let's say, that the pyrolysis of plastics or tires is a reverse process of the really production or in the nature of hydrocarbons in the ancient years, a million years ago. So we took the polymers of the plastics and we make the monomers out of them through pyrolysis. And especially from plastics, we produce a big part of the products is an oil, which is, as a matter of fact, is hydrocarbons, a blend of hydrocarbons that are similar to conventional diesel, with some problems, of course, and also can take a part of naphtha, as a matter of fact, which is has volatiles inside. But the final product has a lot to do from what was the feedstock. You have a single polymer or had a mix of waste, for example, in order to see what will be how good it will be to be used as a diesel blend. So as a matter of fact, it seems that we use the pyrolysis, we use it also for chemical recycling, which is something significant for the plastic industry. But we also think that the plastic waste is the best feedstock, along with the high density polyethylene for producing a fuel grade, let's say, pyro oil. But some of the plastics like PET and PVC, we cannot use them because they have problems in the fuel lately. I won't stay a lot on this part. As I said, it has similar properties with the conventional diesel fuel. And of course, there are things, I don't say a lot of that, but about production, there are issues in production because in general, the idea is simple and it's easy to proceed to pyrolysis, but to make this process feasible economically and practical in a way, and especially physical in an energy, from the energy part, it's not an easy thing, especially when we talk about batch processes and simple plants. And as a matter of fact, the final oil that we have, we must also purified them and make to pass it from a special final, let's say, process in order to part diesel from gasoline part. I mean the volatile parts from the non-volatile parts in order to purify it and can use it as a diesel substitute or blended diesel. So we also could have changes in the emissions from that. Some emissions are better, but some others are not good, like NOxes, for example, which we have to deal about that. But we have a very good behavior concerning PM and smoke, as a matter of fact. So about its sustainability, as it's from recycled carbon, in RED 2 we have a special definition about these fuels. It's not a direct reference to pyrolysis oil, but European Union considers that all fuels coming from recycled carbon, they are considered 100% renewable. And the future, of course, is e-fuels, synthetic fuels that are produced with electricity from renewable sources, water and carbon dioxide, which will be considered 100% sustainable and zero carbon. But these e-fuels, of course, they can be used in the existing infrastructure, and this means that also we don't need to change supply chains and also internal combustion engines in a way, and also not only transport but in the heating market as well. And this is very good. The technology is not yet mature in all streams, as a matter of fact. And of course, we have barriers in feedstock supply chain. We don't have the carbon that would be captured from internal combustion engines. And of course, we don't have this availability of green electricity that we need for these huge amounts of energy that are contained in conventional fuels. So for transport, the main product that we consider that we will use will be methanol, which needs very low modifications in little modifications in the engines, and it can be even used. It's considered to be used in the maritime business, in shipping, with some, of course, modifications. And another concept that goes methanol, of course, is flammable. It has the behavior of a gasoline, let's say. So concerning now production routes for e-fuels, we start with hydrogen electrolysis. This is the main idea. After we have the renewable power, renewable electricity to produce hydrogen, and then with carbon dioxide, that is carbon that is captured, from other anthropogenic activities, we can have different streams with different production processes. Like, for example, we can have methanol synthesis. We can use Fischer-Tropsch to produce gasoline, kerosene, and diesel. We can have methanation in order to produce methane and then bio-LNG. And of course, there is also always the Haber-Bosch process to produce green ammonia. And I won't stay along with that. There are already specifications, especially for biodiesel, bioethanol, and the conventional fuels. We can see both specifications for the pure product and also specifications for the blend. For example, we have for gasoline, there is the European EN 228, and that also defines that there can be a content of bioethanol or bioethers inside, and also EN 590, which is for diesel, and also says that it can the blend can have 7% biodiesel without the consumer to know about that. But also we can have now we have specifications for higher blends for both gasoline and diesel, and for pure as well. The specifications are there in European Union and the United States as well. The real problem is that for higher blends, we don't have, let's say, the tax processes and all these that we need for delivering the product to the consumer. And movements like that, we have specifications also in other countries like India, China, Japan, etc. And so all over the world, we have specifications for that. This happens also with renewable diesel and renewable fuels of second generation as well. So this is from me. Thank you very much for listening.
Thank you, Nikos, for this very interesting overview of the biofuels technology and the productions. So any questions? I think just, yeah, please, Michelle.
Just to use my here.
Yes, but I wait for my.
Okay, so thank you for the presentation. I'm wondering on some aspect of the Power-to-X technology that you mentioned. A couple of years back, I was involved at the European Commission as well, and I remember that it was a little bit more complicated for Power-to-X fuel to be considered as advanced renewable fuel. Is it still the case? Because if we compare like e-fuels to classical biofuel, was a little bit more tricky or trickier to get e-fuels to be considered as advanced renewable fuel as compared to classical biofuel. Is it still the case?
It's always the case to proceed to a life cycle analysis in order to be sure that you have the sustainability over 70%. So this is the main idea. So considering e-fuels, I think that it's not the subject because already in the Fit for 55 bundle of directives, we know that we must use RFNBOs, and there is a mandate for that. I mean, with a percentage, mandate with a percentage that goes even up to 2050. So we must use it. But when the time will come, of course, sustainability will be a great issue in order to see what is the process, what is the energy efficiency, how we did with the carbon capture, because this is the main part, how green is the electricity, so on. So for every stream of all these new fuels, sustainability is always the first issue to examine. And we cannot proceed if we have something, for example, like more than 33 grams per megajoule. So it is always an issue. But I think that from the time that the European Union has put RFNBOs in a mandate, they believe that this is a future and we must proceed to that.
Follow-up question. You mentioned as well that the technology is not there yet. I don't know where. I've been talking with the guys at Carbon Recycling International in Iceland, and I think they have like first-of-a-kind infrastructure there, or is there still demo scale of their infrastructure?
Well, at the moment, I don't know any facility that is in industrial scale. Okay. So the technology is there. Of course, we know for Fischer-Tropsch, for example, producing Haber-Bosch for ammonia, it is there. But it's not an easy and it is an expensive technology, and especially when you move to large scale and industrial scale. So there are no big facilities at the moment, but there are a lot of, let's say, projects that are not have not implemented yet. But I think until 2030, we will see e-fuels in industrial scale, not in availability such to let's say to substitute all the other fuels, but this will, for the European Union, I think they believe that this will happen after 2035. So the technology is there as a technology. Fischer-Tropsch is an ancient technology from the Second World War, but still to use it, it's much more expensive than conventional fuels. When we compare that with the biofuels, conventional biofuels, biodiesel, for example, or with pyrolysis oil, which is cheaper than conventional fuel. So when you take waste, it's easy. When you need all this green electricity, which is huge terawatt hours, literally very big amounts of electricity, it's a question where we'll fund it and in which direction we will send them to industry, to fuels, to transport, to aviation, to shipping. We have a lot of needs in green electricity, and e-fuels need a lot of green electricity, and also with carbon capture, we have nothing at the moment. There's not only some pilot projects. We don't have an industrial project and also supply chain of carbon that is captured from carbon dioxide. I mean, so we must build green electricity projects, huge green electricity projects, huge carbon capture projects, and then proceed to e-fuels.
Okay, can I ask another question? Why not, right? So on the plastic pyrolysis and conversion of plastic into fuel, what is the vision in RED II, or what is the vision of the European Commission concerning the use of plastic? Because on our side, it's always tricky. When you're talking about plastic, I think they prefer to landfill that instead of trying to make fuel, because they say, oh, it's evil to make fuel out of this, but otherwise you're going to landfill or burn it. But no, don't make fuel. So what is the vision of the European Commission on this, or what is the vision here right now in Europe?
There are two parts with plastic. I mean, the one is that we need to reduce the plastic use which is something that we do not see very feasible, not we, the whole world, because our civilization is really relying on plastic. It will collapse. It will, imagine this room, if we put away plastic, there will be nothing. Okay, so the problem is that there is a very big need to make sustainable the plastic industry. It means that we must proceed, and this need for that, to proceed in industrial plastic recycling. This means that we'll take the polymers, make a monomer, and then we proceed again to the polymerization of this specific stream, for example, for HDPE or polystyrene, for example. But the problem is the waste. The waste, which is, plastic bags, etc., what we found in beach, everywhere in the fields, for example, have a lot of, and this cannot be turned to a monomer in order to supply the plastic industry. So we can close our eyes and see, okay, there is no plastic waste, but there is a plastic production about 450 million tons each year in globally, and we recycle now less than 8% or 10%, something like this. And there is no, it's not easy to recycle more. To recycle means to become plastic again. So we'll still have a trend, an upward trend for plastic production because of the countries that are the development now, the Southeast Asia, etc., and the big population. And we cannot see what we'll do with the real waste that goes now for landfills. So yes, we understand, I understand personally, let's say, but this is oil again. Yes, this is oil, but this is the recycled oil. So you use it twice, and the carbon dioxide from this plastic will go again in the atmosphere, maybe 10 years or 20 years, but will go again out. If we can limit the plastic use, it's fine with me. It's excellent, but we do not use it as a matter. So it's better from burying it in a landfill to reuse it with the combination later on of a carbon capture devices. So we'll use the plastic, and instead of putting that in the atmosphere, we'll reuse it for synthetic fuels. So all this, it's ideal. I don't know if it can really happen. I think it will happen, and because it will save energy, and this will be the most efficient thing. And recycling plastics is cheaper than doing any other renewable source. So my experience and the world's experience is that always the industry will tend to something that is cheaper and more efficient in energy and economy. So I believe that from the next 10 years, we'll see a lot of development in this field.
Many thanks.
Okay. Thank you very much. Thank you.
So, I think that after hearing that Panos and Nikos talks together with the discussion, I think that we're entering the carbon hype. Either if we talk about biofuels, we have to see where we'll find sustainable carbon, or synthetic fuels. Where to find sustainable carbon. And for biofuels, we need the soil carbon to be there, to be saved, so as to secure sustainability and so on. Anyway, so we move to our next, let's say, session, where in CERESiS we had the pleasure to be one of the 3 projects that were funded from the same call by the Commission. Were 3 projects on the same call, all focusing on phytoremediation for use in biofuels, and we managed to do several meetings and events together. We co-organized things, and that was really nice because we actually covered the entire palette of phytoremediation techniques, pollutants, and technologies for biofuels. So we have 3 brief presentations, each for each project. So first is Thanos, the coordinator of CERESiS, and then we follow Effie, the coordinator of GOL, the second project, and then we have also Lucas as representative of Fit to Climate. So Thanos, please, the floor is yours.
Thank you, George. So Thank you all again, once again. This is a brief overview of the project, CERESiS. There is more detail on everything I'm going to discuss in the second part of this event. I'm going to keep it brief. What I would like to highlight here is that we had two very interesting invited presentations. The first one from Dr. Panagos was on the upstream part of what we're discussing. So it was how on the soil and contaminated soil and the situation of that, the health of soil. We had a very interesting presentation from Dr. Yapis on it was the upstream side, and now we have the downstream side with the biofuels and how biofuels can be produced. And CERESiS and the other two projects are about bridging these two areas, so connecting these two. So the key aim of CERESiS, similar to the other projects, was to bridge this gap and use the contaminated land productively to produce biomass, and then biomass can be converted using several technologies into clean biofuel. And by doing that, we have a win-win situation where we phytomanage or phytoremediate land, depending on how we approach it, while at the same time producing something valuable that we are currently missing, which is biofuels. CERESiS was structured along three objectives. The first one had to do with investigating the behavior and effectiveness of conventional and novel species of energy crops for phytomanagement and phytoremediation. The second had to do with developing the appropriate technologies for converting these energy crops into clean biofuels, including also separation technologies. And the third one had to do with providing decision support into key stakeholders and policymakers to be able to achieve that, to develop the value chains that are needed. It was a project, or it still is a project, of 12 partners from 8 different countries across the globe, including Canada and Brazil. So a quite international project. And this is how it is organized. So the three objectives are reflected into 3 pillars. The top left pillar had to do with phytoremediation and development and a several number of trials across the world. We had trials in the UK, Brazil, Italy, and Ukraine. This created a lot of knowledge and also several samples of biomass that were fed into the bottom left pillar, which is the technological pillar. So we had a lot of trials and we tried to optimize the technologies in order to be able to use these contaminated biomass samples, and so that contamination is not, it does not move into the final product, so that we get a clean biofuel in the end that can be usable, and we can get the contaminants in some sort of concentrated or manageable form. And both these pillars provided information that was used in the decision support pillar. We developed a decision support system that we're going to demonstrate in the second part in a live. So I'm not going to talk a lot about it now, but it uses a lot of novel techniques like machine learning, like supply chain optimization, life cycle analysis is embedded, and we have a multi-criteria perspective, which means that we assess a number of pathways. By pathways, we mean combinations of energy crops and technologies for each specific location or contaminated land case, so that we can come up with optimal approaches or pathways. This is just an overview of the value chain that is involved. As you can see, the invited speakers covered the upstream part with the energy crops and the downstream part with the biofuel production and use. So the project covers the full value chain. There's a number of different stakeholders involved, as you can see here. And starting with the upstream part, CERESiS used perennial grasses primarily. So this is the key, not only perennial grasses, but this is the key focus for phytostabilization. And the key idea here is, you're going to listen also later on, is to maximize the biomass yield so that we have a lot of production as much as possible for economic sustainability. Because if we do something in the long term, it has to be economically sustainable. So maximize the biomass that we get from this land, the contaminated land. We minimize the uptake of contaminants in terms of contaminant uptake per kilo of biomass, per unit of biomass that we get. But ultimately, because of the high production volumes, we maximize the contaminant offtake from the land. Even if the biomass has little concentration in it, removed from the land is quite significant. And the key focus is on phytomanagement primarily. And these are some pictures from the trial sites. You can see biomass growing happily in several countries. So top left is the UK and the Canary grass. The bottom left is in Brazil. Top right is in Ukraine, Canary grass and miscanthus. And the bottom right is in Italy. The second pillar was about technologies. The first technology investigated was supercritical water gasification. The original challenges were that the carbon efficiency was quite low, below 75%. We had blockages in the experimental devices because of the nature of the biomass used, and formation of coke and reactors. After a significant number of experiments, 103 experiments were carried out, and several redesigns of the lab facilities was performed by our partners. The final result was quite interesting because we had a high gasification efficiency achieved, over 90% carbon efficiency. Our partners were able to achieve long-term operation without any blockages, and they identified the optimal parameters determined. Downstream of this process, there was hydrocarbon reforming and Fischer-Tropsch synthesis investigated, and in this, our partners achieved a complete methane conversion, and also they investigated the use of structured iron catalysts using 3D printing methods. And finally, there was a Fischer-Tropsch synthesis achieved for over 100 hours of operation. Regarding the second technology that we use, which is pyrolysis, there was an optimization of the operating conditions of the plant achieved for the types of biomass that we looked into the project. There were 15 experiments that investigated 3 key parameters like temperature, carrier gas flow rate, and solid residence time. Please ask the online participants to mute their microphones. Can you please mute your microphones because there is some noise? Can you please mute your microphone? The online participants, there is some noise. Okay, the novelty here was that optimization was carried out considering at the same time the liquid yield, but also the contamination in the fuel. And also the performance of the pyrolysis plant was optimized. There were 8 experiments for 8 different types of biomass, and the key achievement was a yield of liquid bio-oil between 30 and 40%, with very low solid content and contaminant content, which is quite a good achievement, a good result. At the same time, there was quite interesting research performed on utilizing lower heating value gases produced from pyrolysis within the process, or generally exploiting them. So the partners achieved an exploitation of gases with lower heating value over 3 megajoule per kilogram, which is quite interesting, with low NOx emissions and CO emissions. And therefore, they proved that the mild combustion is a very flexible and resilient process that can be embedded in pyrolysis gas composition. At the same time, separation technology microfiltration was used to remove the solids from the bio-oil quite effectively. So there was no fouling of the membranes, and even if there was fouling, it was reversible. And we had a very good result in terms of retention of carbon particles in the bio-oil. So bio-oil was effectively cleaned by this process. Continuing with decontamination, there was also a membrane gas absorption process developed to treat the supercritical water gasification gaseous product. And this was performed here in CERES, and it was quite effective in capturing hydrogen sulfide, and also there was significant CO2 removal potential using this technology. So quite good results in this respect. There was also a hybrid electrocoagulation, flotation, and electro-oxidation process developed to remove the organics and heavy metals from the brine of supercritical water gasification to clean it up, which proved also to be quite effective and with relatively low energy requirements. So all these technologies can ensure that we get, in the end, clean biofuels. So we remove any contaminants that pass through the biomass. In the process, we remove them at the thermochemical conversion stage, and we can get clean biofuels in the end. Finally, the third pillar had to do with a decision support system that we're going to demonstrate later. This is just some key informations. We're talking about decision support. So what kind of decisions can this system support? The first one is which biomass types are suitable for a particular contaminated land conditions, considering both the soil characteristics and also climatic conditions. The second type of question is what are the expected yields and contaminant uptake of these types of biomass? So this is quite interesting if we want to investigate what to do with this biomass. The third one is which combination of technologies and biomass types are suitable. And to be honest, we found that our technologies are quite flexible based on the experiments that were done. And the fourth one was what is the optimal supply chain design? So where should we locate facilities if we are going to do this commercially? What should be the capacities? What should be the structure? What should be the flow of materials within this system? Because there are many ways of doing this. There are more expensive ways, there are more clever ways, and this is where we employed optimization tools. The fifth question is what is the optimal value chain configuration for the specific conditions that we're investigating? So the user of the decision support system can import location-specific sites and get some responses. So, for example, which biomass type they should select, which technology they should select, which supply chain structure they should select. So the whole value chain, the optimal value chain is proposed. And various value chain options are also ranked and offered to the user. And finally, what is the performance of all these value chains against three different dimensions of sustainability? So the results have to do both with economic, with environmental, and also with social KPIs. So we assess all these three aspects of sustainability of the various value chains that we can investigate. This is the flow of logic of the decision support system. For the sake of time, I won't go through it. The key elements that are included is a machine learning element for biomass suitability. So we have fed the decision support system with the data we collected through the project and also additional data from the literature as much as was available. And we employed machine learning techniques in order to be able to predict what will happen in a new case that the user will enter. The second one was technology suitability assessment. And as I mentioned, our technologies are quite flexible as we discovered through this project. The third one was supply chain optimization. The fourth one is the life cycle analysis of the various pathways that we investigate. And also assessment of the social impact, which is quite novel for these cases in these value chains. Finally, there is a multi-criteria analysis module that helps the decision makers in making an informed decision. Regarding the policy aspect, there has been some work on this front. We have engaged with various types of stakeholders during the process of this project, from the EU level, institutions at the EU level, like JRC, EA, CEN, and also various value chain stakeholders represented either through the External Advisory Board or through other means. And some of the key findings is that, firstly, there is not an overarching legislative framework in place currently that links these two sectors, the land decontamination, the soil decontamination, with biofuels. So currently there is nothing there in this respect, and therefore there is a need for a support and legislative framework to be adopted, so there is a common framework for these two sectors. And that the proposal the directive on soil monitoring and resilience, as was mentioned also by Dr. Panagos earlier, provides a unique opportunity to make this happen, to link these two sectors. So this is a brief presentation of CERESiS from my part. Thank you very much for your attention. Not sure if there are any questions. Probably later when you'll hear more about it, you'll have more questions. And I would like to invite Dr. Effie Alexopoulou to present the GOLD project. Okay, I'll find the presentation for you. Go.
Thank you, Thanos. So good morning from my side. I would like to thank you, Thanos, for the great collaboration the last 3 years. We actually became friends and collaborators. That's very good from now on. And I would like to thank you a lot, Sir, for being in Gold, but at the same time for hosting this event, and also George for the kind invitation. This is, I think, the third event that we were working together and trying to present and compare the 3 projects that actually were funded by the same topic. Sorry, please. So you will see several similarities with CERESiS, but if we put the puzzle, the 3 projects, you can see later on from Marcus, we can collect very valuable information, because although we have several similarities, we can say that we can be complementary. This is the starting point. Please consider the proposal was written, the project 4 years ago, it was 2020. Many things were different. What is not changed is the contaminated land. You saw from Panos Panagos how big, important issue is the contamination of the soil. So this remains, and at the same time, those we producing biomass, we want to avoid the competition with food products. Nikos Liapis said about that, about the first generation biofuels. So what was the aim of this project? Were to go on contamination sites and produce biomass, and at the same time to try to decontaminate, if possible, the soil. It's not an easy procedure, but it's an issue it's a problem, but for us, it's also an opportunity to produce biomass. So, more or less, the objective were the same, since the topic was the same. So, one work package, it was devoted for the production and remediation of a selected contamination land. The second was the production of clean liquid biofuels, because this was what we want to prove with different technologies. And the third was the bridging the gap between phytoremediation and clean liquid biofuel production, and if possible, like Thanos did very well, to develop tools like decision support system to make some predictions in the area that we're going to work. Of course, dissemination and management. In Gold, we have 3 pillars. The first pillar is the optimization of selected high-yielding lignocellulosic crops, but for phytoremediation. The second pillar is the technology that we use to produce the clean liquid biofuels. And the third pillar, as I mentioned before, how to bring these 2 big issues together and how to make some scenarios for decontamination. We want always to produce low ILUC feedstock for low ILUC biofuels. So, 2 phytoremediation strategies, because we want to cover both heavy metals, organic and inorganic pollutants. 2 phytoremediation practices. We use mycorrhiza and biostimulants, and some graphs you can see about this. Again, the 3 pillars. If we go again to the first pillar, we can see that we have several contaminated sites. You can see later on in Europe, but also in Asia, like China and India. And we have 2 conversion routes, one organized by European partners, the second by Canadian, and the third is the bridging the gap and the combination between the sites, the treatments, and the technologies. What is an important element in Gold is the mapping of the contamination land. At least we try to do a first attempt. You saw in the first presentation that now, the last 2-3 years, a lot of activities are focused on the contaminated site. So when we try to write gold, we thought that there are no maps that we can find very detailed, organized, where are the contamination land. So Wageningen University tried to mapping this area. You can see one graph later on. But which were the crops that we selected? I mentioned that we want to have high-yielding lignocellulosic crops. Why this? We want to make biofuels. We want a lot of biomass because there is always the possibility to use a plant that is accumulates a lot of heavy metals. But if they produce half a ton of biomass per hectare, this is not sufficient. We want to have a high biomass production and at the same time, the crops to be able to uptake heavy metals. Usually the lignocellulosic crops, they consider excluders, but we try to select those that they combine both of these elements, high biomass yield production and some heavy metals uptake. So we selected miscanthus and switchgrass. I think that in CERESiS you have both of them, miscanthus. I'm not sure about switchgrass. You have red canary grass, but miscanthus is common. And we have two annual crops, sorghum and hemp. So if we see which crops are similar with CERESiS, I think it's only miscanthus. Based on a previous project, Magic, that we tried to see what should be the protocol of cultivated lignocellulosic crops, we follow the proper agricultural management for successful phytoremediation. And finally, we put emphasis on having a common protocol on the fields in order the results to be comparable at the end of the project. So more or less, all the partners doing these field trials, they had to grow 3 crops with the same protocols for a period of at least 3 years. And now it's the 3rd year starting doing these field trials. But which are these sites? So we have 2 sites in Greece, one in Poland, one in Italy, and we have actually 2 but in France, but we have one in France plus one expert that is bring us a lot of information. So in order to do the bridging the gap and to develop scenario, we thought, okay, a pool of source is the real field data. But if the project starts has a duration of 3-4 years, how many data you can collect? And it will be 5, 6, 7, 8, 9 sites. So it's not a lot of data to make predictions. So we thought to include some experts, additional experts, that they have long-term experience on phytoremediation, and this expert brings their expertise in this scenario that now we are developing. So from the project, we have 5 real sites in Europe and 3 in Asia, 2 in China, 1 in India, and more an expert from University of Kassel, professor, an expert from France, and also from Portugal, that they are going to help us. I mentioned before that we're trying to do the mapping. I put this slide only if you want to visit the website of Gold, you can find this deliverable. And this was presented as a plenary last year in the European Biomass Conference in Bologna. You can read it and understand what we're doing. We try to distinguish the contaminated land between diffusion pollution and point source pollution. It's not an easy task because the information that was available, it was very few. And go to the conversional routes. So all of us will have to prove that we can produce clean liquid biofuels. But first of all, liquid biofuels. Please consider that the TRL of this topic, it was too low. So we have to produce some innovation. So the ending TRL should be 4 to 5. So all of us, I saw that we more or less, we did a gasification, different type of gasification, and pyrolysis. In our case, the European partners that are CERF, TNO, University TUM from Berlin, and Record from Italy, they try to organize the first route. We have three ways of pretreatment of biomass, of the polluted biomass. The first one, it was the torus technology, torrefaction. Both these two treatments are being done by TNO, and the third is from Record slow pyrolysis. And then TUM is doing the high thermal gasification, and from now on, TUM is doing the gas cleaning and the C-gas production, fermentation. Because I mentioned several times, but during writing the proposal, we were very afraid to mix the partners from Canada and Europe. So we thought the pyrolysis route to be organized by Canada. So in case that they don't manage to take money, to have at least one completed conversional rules. And you can see more details in the other two pictures. Now, what we are doing from torus, we're going to take humic acids, and we're going to go back on pot trials, because I forgot to mention that in the beginning of the project, we start with some pot trials with contaminated soil collected from our site, and we select which were the best combination treatments to apply on the fields. But now we will go back to these pot trials. We will take the humic acid, and we are going to test it as a biostimulants in our for selected crops. And this is going to be to start now, because gold is going to finish in 12 months from now. So in the proposal, we have this idea to create win-win situation, to combine the contaminated site, the selected crops, and of course the phytoremediation practices, that it was not the same for all the partners and all the crops, and to combine with the conventional routes to see what was the best combination. This was from the proposal. But when we tried to work on the project, we ended up to this approach. So we thought to work in detail on the European sites, because the information that we had from Asia, it was not at the same level. And of course, it's not possible with 3 million projects to cover every aspect. So we go on the 5 contaminated sites, and we select the best ligno crops per site and the best treatment. And these, they are combined with the 3 conversion options. The one of European, you remember, with the 3 different treatments. And this is a combination of 15 value chains that now we are working on this. And we have +1 that comes from Canada, because Canada has pyrolysis and take biomass, produce locally there, but it's not so contaminated like the European one. So if we say in a nutshell to see what are the main messages of gold, we work in detail on 4 crops, but now we added an additional 2-3, but just to enlarge the knowledge that we're going to have from the project. We completed the 2 years, and now I saw the results. They are very promising, and we continue with the 3rd year of field data. Now it's the time that we have the real data, because we deliver the feedstock to the partners of work package to do the big trial, and we are going to have a nice result, at least the first indication by October. In the next meeting, we will be able to develop to produce a lot of information. Remember that we have 2 conventional routes, and we are going to develop optimized phytoremediation solutions, but these solutions are come both from our project, but from previous data from the experts that we have in the project. We organize 16 value chains, you saw that, 15 European, 1 from Canada, and we will see if we have time to add also 1 or 2 value chains from Asia. And finally, as all of the projects funded from the same call, we had to do international collaboration. That's why we have India, China, and Brazil, and we want to contribute to mission innovation on biofuels. The consortium, in yellow, you can see the partners. In blue, you can see the members of the advisory board. And of course, you can see the logo of our partners. Thank you very much for your attention. And thank you again for the kind invitation.
Are there any short questions, or we should probably move directly to the presentation of Fit to Climate? So I don't know if we have Marcus or Lucas with us.
Can you hear me?
Yes. Hi, Marcus. Good morning.
Hi, good morning. Good that this works. Perfect. So I will start video. See?
Yeah, we can see you as well.
So, okay, perfect. So then I will try to share screen. Let's see if this also works. So, can you see anything?
Not yet.
Okay, then to start. Can you
Yep.
see?
That works. Yes. Thank you.
Oh, wow.
Of course,
Great.
yours.
Okay. Yes. Good morning, everyone. Also from my side, it's really a shame that I'm not able to be physically at your final event in Thessaloniki. But I'm very much sure that we will find very soon another opportunity, for instance, in 2 months in Marseille, hopefully. My name is Markus Ortner. I'm from Vienna, Austria, ITS, and I'm the coordinator of the Fight to Climate. Thank you very much for this kind invitation, even if I can only be or join for a short time and only virtually. In any case, I wish a great team of CERESiS, let's say all the best, a great final expert of the project, and finally, of course, also smooth project completion. As the panels and FB already outlined, we were applying and submitting in the same call. That means our objectives are more or less the same. So we want to have clean, or let's say stabilized soil conditions. On the other side, some added values from the let's say from the biomass generated there. So, and I would also like to use this opportunity to squeeze our project in this next 10 minutes a bit, and first give you a short overview. Next slide. Perfect. To transform situation as shown here on the left hand side, this is actually a slide from one of our partners in Argentina. To the situations shown on the right hand side, there are different technologies, standard technologies, I would say, on the market. Most of them, they have disadvantages. As we know, they are invasive, and they are also, in certain cases, also very cost efficient. And this was actually the starting point of our idea to develop a cost-efficient approach, which is given by achieving two benefits at the same time: a healthy soil on the one hand side, or let's say it another way, stabilized risk of environmental risk of this contamination. On the other side, added value products, for instance, in form of biofuel. The key for this, and we have heard it already in the other presentation, is definitely at the very beginning, the bioremediation. So, okay, Here on this slide, you can see our project in a nutshell. Just quick, it's based on two pillars. I would say we have a technical pillar, which consists of the generation of the biomass by means of phytoremediation, and includes also, of course, the remediation activities and also the stabilization of the contamination. And the second part is the conversion of the harvested biomass into added value products. On the other side, the second pillar is very much focused on different aspects, starting from social acceptance, of course, greenhouse gas emissions along our value chain, balance, and very importantly, of course, the legal and the regulatory aspects, and which is very much connected to the development of a business case or business model at the end. In the center here, you can see a very crude rough scheme. In the bottom line, you can see the remediation process. At the end, we would like, all of us would like to have a remediated arable land. In some cases, probably this won't be the case, but at least we would like to have a stabilization of contamination, so that the environmental risk is definitely reduced to a minimum. And then you can see two routes going up. One goes to the right. This is the conversion process, ending up in the drop-in biofuels, and another one where we also use an outcome and output of our conversion, the solid fraction, which is introduced in the metallurgical industry. And yes, I will show you a little bit later what this means. What else can you see here? You can see our geographical distribution of the consortium here. So we are very much focused in Europe, but we also have countries, partners outside Europe, for instance, Serbia, and also Argentina and South America. We started at the very beginning with 17 partners due to the very difficult situation during the pandemic. We lost, unfortunately, one partner in India. And yes, on the right hand side, you can see our phytoremediation pilots. We have 5 pilots in Argentina, Serbia, Lithuania, Spain, India. As I said, India we lost, so we are at the moment, or in the past 3 years, we are operating 3 pilots. In red, you also can see the contamination which is present at the pilot site. Yes, so the very start is the phytoremediation. So FB Panos already said a lot about this. It's more or less from the methodology a very similar approach. So we started in lab scale, in small scale. So the idea, the objective was to find, of course, the most appropriate, the best prop setup, which is able to cope with the contamination, with the, let's say, the setting on site, and to transfer this setup, the best optimized setup, then to a bigger scale, to the feed scale, where we investigate the other 2 projects as well, parameters such as reduction of the contamination, of course, but also a very important parameter, also the specific biomass used by hectare, for instance. And what else is important in our projects? We also try to define, to develop a soil quality index, which might help us to make some extrapolation of the data what we generate for the, let's say, 2, 3, 4, maybe 4.5 years, because as we know, such a remediation process, it takes quite a while, and yes, it's not such an easy task to say, okay, that's what we achieved in the past and the first, let's say, 3, 4 years. How will this develop when we look to, I don't know, year 10 or year 20? And this is also one of our activities in our project in this field. Here, in this slide, I will give you just a rough overview about our phytoremediation pilots. You can see Spain, Lithuania, Serbia, Argentina. You can see here in black, the black boxes, what it is, where the contamination is. In Spain, for instance, it's an industrial park. The contamination is TPH, it's petroleum hydrocarbons. A similar issue we have here in terms of contamination in Lithuania, but it's not industrial park, it's an urban area in a small city. In Serbia, we have heavy metal contamination. It's a specific case here. We have a very long canal to the border of Romania, and this is, the sediments are contaminated with heavy metals. They will be dredged by annual basis. And yes, and in Argentina, this is a really heavy case. You can see here it's a former gold mine, and you can see nothing is growing there at all. It's a bit outside in the countryside, so you could assume nobody's living there, but it's not the case. So behind these areas, there are local communities living there, and apart from our field sites where we test and try to implement remediation activities, there's also in parallel social projects ongoing where we invite the people living next to them, because they have agriculture there. So not of course in this area, but very close, and still in this area you also find contamination, and this is really yes, dangerous, of course, because the vegetable what they are cropped, they are containing this kind of heavy metals, and here we try to engage them, to work together with them. They are also in some parts involved, so they can learn from us, and on the other side, we also learn from them, and this is quite interesting synergistic collaboration. What you can see here is also the type of crops what we are planting in the different pilot sites, and in the clouds you can see, for instance, one of the parameters is the biomass yield compared to biomass yields on non-contaminated soil. So you see, so we are here in Spain a bit more of 70%. In Lithuania, we achieved, even went over the 100%. Similar situation in Serbia. But we only achieved about 50%. This is definitely the case, because the reason is definitely that the contamination is really harsh here with the arsenic. You see 6.5 grams per kilogram, so this is quite high. What else you can see here, the TPH removal is about 86%, for instance, in Spain, 72% in Lithuania, which is quite good. And if you look to the translation factor of in terms of heavy metal uptake, you can see we are for certain elements such as lead, zinc, copper, and any others, we are also able to achieve a factor higher than 1. Okay. Yes. So what after the harvesting, so we are converting this biomass, and our approach is to valorize, to utilize the entire biomass in our biorefinery pilot. The base is the thermocatalytic reforming step, as you can see here. This is, I would say, in principle, a pyrolysis step where we reduce intermediates, a gaseous phase, 2 liquid phases, and solid phase. Subsequently, then further refined, and this we can see here a bit in detail. You can see here in blue the intermediates, it's the aqueous phase, it's the gas phase, it's the second, or it's the oil phase. Then we have here the solid phase, and in case of races, for instance, which we are also using, we are of course also using the seeds. And yes, and here in orange, you can see the products what we have proposed in our approach. It's the biodiesel, diesel gasoline, it's a marine fuel, and it's a char. And yes, let's have a look. I mean, this is not rocket science. This is something which is has been established in the past 20, 30, 50 years. So, but we have shown that the requirements for biodiesel Also, these crops were grown on contaminated sites and are achieved. So this was done. Next one, and this is always an issue because people who are usually working with this kind of technologies, let's say, not really using this water. Mainly, it's that okay, they use it for irrigation purposes, but this water contains a COD level, which can be also quite high. In our case, we are using an electro-oxidation process step where we generate a hydrogen, and we were already able to show a reduction of almost 94 or let's say 94% of reduction in a, let's say, proper appropriate time window. Of course, you can also bring it up to probably 98, 99%, but this is in terms of economics not probably a good choice. So this works. So this is good. So we're quite happy with that. The next one is the gas phase. So here we introduce or proposed a GTL step and started actually with the Fischer-Tropsch. And here the crucial part is always the gas cleaning, because the catalysts which are used there are quite sensitive against certain compounds in the gas. And this was for us the tricky part and took us quite a lot of effort. It works, but at the end of the day, we were changing our strategy because the effort to use this technology is quite too high, especially when it comes then to the economical perspective. Therefore, we changed our strategy from hydrogenated compounds to oxygenated compounds, which is an intermediate still. But at the end of the day, we will supply this or provide this material in our thinking then to our existing refinery, which can then be hydrogenated and then used as diesel and gasoline. And the process what we are now working on is the so-called phenol process, and where the catalyst is much more stable and robust. And of course, we need also gas cleaning, but it's not comparable with Fischer-Tropsch. Yes, next one is the oil phase. Here, our aim was to do a distillation step and to bring them or to be used then at the end of the day as a marine fuel. This works well. Here you can see that for 8217 fuel class, the requirements in terms of kinematic viscosity, and here you can see one of the outcomes. You can see this works quite well. So requirements were achieved. We are quite happy with that. And finally, we also produce here in our process a solid fraction. It's the coke, where most of the heavy metals, in case of heavy metals polluted biomass, is accumulated. And here we are able to cycle even some of the metals. This jar is used in a copper smelting process. One of our partners is the world's biggest copper smelting copper recycling company, and they have a certain step in their process where they use petrol coke, and here we are able to replace this petrol fossil-based coke by our, let's say, bio coke. And yes, so the reactivity, this is one of the parameters, or among others, which are measured there. And in certain cases, the reactivity is up to 30% higher than the petrol coke, which is actually a good outcome for them and was also for us. Yes, as mentioned already at the beginning, apart from the non-technical activities, our approach addresses also non-technical aspects. All three topic areas play an important role, especially when it comes to questions related to the implementation of such a technology. All of them are very strongly connected to each other. Yes, it's of course along our value chain. So we are looking to what is our environmental impacts. As you can see here, our system boundaries, what we have defined as for the remediation, then later on as for the biomass processing, for the conversion. So it was a big work at the very beginning, and then when it was finished, this was fed, let's say, by literature data, but then later on, so we replaced them by our real data from, for instance, from the biorefinery plant, but also, of course, from the phytoremediation activities, and we do iteration by iteration, and our let's say results, of course, are changing, but they are somehow much closer to reality as it was at the beginning with the literature data. Yes, the second one is a very important one, and we have a really strong focus as there is environmental law institute on board in our consortium, which are really focusing on a bunch of questions. Questions could be, okay, crops for phytoremediation, because in different countries you have different situations, different laws are implemented, so they are checking them. So are GMOs, invasive species allowed or not? So what does the law say? The countries where we are looking are, of course, Spain, where Ukraine, Serbia, and Argentina. Apart from them, we are looking also to Belgium, to England, and also to Brazil. And of course, we are also looking in the or try to find questions also in the EU context. Yes, domestic law, phytoremediation somehow listed in the domestic laws of the countries as a soil remediation. What about waste legislation? What about the outcomes? What about the output materials which comes from the phytoremediation process? The contaminated, how is this? How does the legislation look like, and so on. And last but not least, and this is of course at the end of the day, the economic, the business, of course, is something very important, and yes, and therefore we are very much looking to the market, to where are the driving forces here, and the big impact parameters. Who are the stakeholders actually? How are the attitudes of the stakeholders? How was it in the past? How is it now? How could it be in the future? And so on. And at the end of the day, we are trying to not to have a business model ready to roll out. Of course, we are at TL 3 to 5, but that we would like to have at the end of the day a strong base of a business model, let's say, where we can make a decision for our overall project to say, okay, this is a good thing. We would like to continue, or we have to stop it. And yes, and yes, none of this would be possible, of course, with a great team that do a very excellent job. Big thanks to everyone who is involved in this project. Here in this photograph, you see some of our team. Our team is much bigger. There are a lot of helping hands and technicians in the back, which are not here in these General Assembly meetings. I also would like to thank them. And yes, so this is the end of my presentation. Thank you for attention, and if there are any questions, I'm happy to answer them.
So thank you, Marcos. We're a bit behind schedule, so we will skip the question to food climate at the moment. Maybe we can have a chance to discuss a bit later. So I would like to kindly ask Kyriakos Panopoulos, who I think you all know, since he's affiliated to CERES, to present us a very interesting project of how to turn food waste, I think, into soil improvement, but Kyriakos will tell us more. We have invited, just to let you know, it's Kyriakos, and then we have also Thanasis Mavrikos from NTUA. And these are two projects from these two good colleagues, which projects are related to some aspects to the collective work of the CERESiS Fit to Climate and Goal. And we thought that it would be very interesting to hear from them what they're doing and see how synergies exist. So, Jacob, please.
Maybe help me around with, probably it will be there. Hello, everybody. My name is Kyriakos Panopoulos. Thanks for the kind introduction. Okay, thank you. So indeed, this project, Waste for Soil, is related somehow because it's part of the soil mission. It's about turning food waste into sustainable soil improvers, improving the food systems, carbon cycling, recycling of materials. This project is now running almost a year. It will be 1 year during this summer, and let me share some details about it. So we did start 1st of June. It's a 4-year project. We are quite big in numbers, 28 partners from 9 countries and Switzerland. Our budget is more than 7 million granted by the Commission, and our, let's say, thinking around the project and how we devised the project is that when looking into the waste generated from food processing processes, food processing meaning not food waste, let's say maybe the title also of my presentation is wrong. So the materials that are wastes from the processing of food, residual materials, is a very big amount. It's a lot of vegetables, a lot of material coming from fruits, from oil crops, potatoes, cereals do have some residues when processed before turning into let's say edible, as well as of course animal-based meat, dairy, and fish products and eggs. So there's a big amount, 129 million tons of food waste generated, and we are only processing a part of it. And that, let's say, material contains a lot of nutrients that could be used and materials that could be used as soil improvers. So we want to use this FPR, these food processing residues, and also wastewaters from the food industry to improve the soil fertility and enhance nutrient use and efficiency. Also minimizing the amount of fertilizers and soil improvers that are derived from classical or let's say fossil-based sources, and of course also create a social awareness for the use of these materials. So we have because we are 28 partners and we have an array of food processing residues, more or less these relate to the table I showed you and the graph I showed you before. We do want to standardize our materials and our soil improvers, and we have around 10 methods of producing materials that after mixing will give us, let's say, soil improvers. This altogether, this would end up in 6 soil improvers. These are also parts of the KPIs of the project. And of course, we are engaging a lot of food systems and citizens, as well as stakeholders in this business. A lot of it has to do with communication and dissemination, and we are also trying, as I heard also in the first presentation today, to create living labs. So within the project, we create 7 living labs across Europe, and these living labs is about collaborating stakeholders, co-creating solutions, and also co-ownership of results. Finding a way of mobilizing the use of these technologies and techniques and applications into real life environment, and of course also providing information and input to EU regulations and paving the way for this kind of circular economy approach for these wastes for the well-being of soil in Europe. So here is maybe a glimpse of how these are spread across Europe.
Kyriakos,
Yes, please.
Kyriakos, sorry to interrupt, but we cannot see your presentation. It's not shared.
Oh, okay. Sorry. Thank you, Kostas. Okay, it's right. As I was saying, now you can see the living labs. Yes.
Yeah, we can see them. Thanks.
Thank you, George, for this comment. So these living labs are spread across Europe, as you can now see, indeed. Also for those who are away, we have living labs in Spain, Italy, and Greece, somehow creating an arts in the south, and then Finland, Poland, and Hungary, going from the let's say top north to middle Europe, including also Slovenia. And we cover a lot of food processing wastes that are being locally processed with various techniques, as I was describing before, ending in elements or ingredients that are ingredients of soil improvers to be created. So yeah, you can see that there is let's say we have different pathways identified. So we do have, let's say, biogas digestate valorization. This is somehow addressed in the Spanish and Greek living labs. Then we have biochar routes. So we create biochar from this food processing waste that's performed in Finland and in Hungary in different contexts. And then we also have optimization of protein hydrolysates in Hungary and in Italy, and in Slovenia we also have microalgae for nutrient recovery from digestate, which is let's say a similar thing because to what happens in Spain and Greece in our living labs. So we have let's say identified similarities between these routes, and what we want to do is we want to use this in a fashion that we use the knowledge of different sectors, and we want to have these soil amenders and the application of the soil amenders, as well as the application of handling this wastes being performed in real life applications from actual users. We are currently setting up the living labs. The living labs is indeed a living organization that the living organizations that are bringing together all the stakeholders into, let's say, a kind of real life test. Although our project is, let's say, low TRL level, some of the solutions we look at is lower TRL level. Still, we engage into this exercise of the living labs. I also have to mention for your understanding that these living labs we have in this project are not part of officially, are not part of the 100 living labs that the soil mission wants to create. But because when we were preparing the application and the proposal, we adopted this methodology of having living labs to support all the value chain of our work. So we created these living labs, but the 100 living labs is a different story, and that is one of the things that also the Commission stressed. So if we exclude ours, they don't have to do 93; they still have to do 100. Right, so that's the message. But we, in all cases, try to operate as much as possible in a fashion of living labs, and that undertakes a lot of the effort. In our particular case, and then I will close. Of course, you can visit the site and you can follow us and get notifications about what is happening in the project. In our case, we work a lot because also of past projects and past experience, also collaborating with members also of the CEF community, Kostas and others in this room. We work on the biogas valorization route. So our part, apart from being coordinators, is mostly looking into this route where these residues undergo fermentation. Then we produce methane or biomethane, and then the residues, the digestate, we valorize by applying separation techniques and coming up with ingredients to be mixed into soil amenders. I hope maybe we have a final event in gold. That some of the results, they are somehow they have something in similar, because here we valorize the wastes. So indeed, this community, I mean, shares some commonalities, and feel free to ask me anything you like after going around the project or right now. Thank you.
You will have a chance during coffee. Yeah.
Yes, the coffee break is.
First, we have to maybe just. Thank you, Kyriakos. So, oh no, I'm looking for. So, is Thanasis Mavrikos online?
Yes, I hope you can hear me.
Hi, Thanas. Yes. So the last presentation of this session before the coffee break comes from the extract project. Thanasis is going to tell us more. Thanasis is from the National Technical University of Athens, and the project has to do on how we can extract, how can utilize or extract mines from mine sites. I'm not sure. Thanasis will tell us, but again, it's still within the sphere of what we're trying to generally do. So,
yes.
Can you please share your screen?
Okay, let me share my presentation. Just a moment. Okay. So, good morning. My name is Thanas Mavrikos. Thank you for your kind invitation. It is my pleasure to be here. And it is a great opportunity for me to present you a sustainable ecosystem for the innovative resource recovery and complex ore extraction, as we call it, extract. Just a few facts for our project. We are a consortium of 14 partners from 9 EU countries, and the coordinator is the Technical University of Freiburg in Germany. We are a young project. We started in December 2023, and our kickoff meeting was held here in Athens in January 2024. This is the map showing the geographical location of the partners and the countries in our consortium. And we have 3 end-user bodies, the pilot sites where the different technologies will be applied. We have 8 academic and research partners and 4 technology, social, small and medium partners, enterprises. The main goal of Extract is to develop a sustainable ecosystem for the innovative resource recovery and complex ore extraction, while providing low TRL green technologies, biomining, phytoremediation, particularly appropriate for mining waste piles and abandoned sites that represent a solution for mine waste remediation, but also for the extraction and recovery of various precious metals. So the objectives of Extract are the automation of mineral prospecting and extraction in a complex mining context, the introduction of the novel concept of precision mining for selective recovery of valuable metals, scaling and deployment of remote sensing system and analytical resources for cases where we have hard-to-access mining sites and waste deposits, enhancement and deployment of a digital repository that would contain some data and enhance interoperability and industrial symbiosis in the mineral recovery supply chain. Also, the evaluation of different mine sites and waste disposals, demonstration of the feasibility of innovative technological solutions supporting a green transition to sustainable mining, the organization and facilitation of the uptake, replication, upscaling of technological solutions developed by Extract, planning and facilitation of the exploitation of project results, and of course, communication, dissemination of the project scientific technical results. Let me share with you some information about our site, the Lavrion Technological and Cultural Park. Well, it was founded in 1992, and the facilities previously owned by the French mining company of Lavrion after an initiative from the National Technical University of Athens. The aim was to host and promote research and business activities. And these industrial buildings have been reconstructed, restored, and they house today a variety of new innovative businesses, some of NDUA's laboratories, and as well as cultural and educational institutions. You can imagine that after more than 100 years of heavy industrial activity in the area, it was heavily contaminated, mostly with heavy metals and other toxic elements. The table on this slide presents some initial chemical analysis of the soil. The values are in milligram per kilogram. And it is clear that the levels of contamination exceed several hundred times the international limits. We have very high concentrations of arsenic, lead, but also zinc, cadmium, and other metals in all sorts of compounds, in sulfides, in oxides, etc. Therefore, there was an extensive remediation program that was decided and implemented, and despite its success in cleaning up the area, we still face problems today because it is a larger, a more wider problem. The surrounding area is covered with mining waste, slugs, and flotation tailings from the metallurgical process. And when it rains, the surface drainage washes many of these pollutants, and the water finds its way back to the park. These two photographs in this slide were taken just 2 months ago. It's in some walls in the borders of the Lavrion Park. And this is basically the focus of our involvement as a pilot in use case 4 in this Extract program. Together with our partners from the Lithuanian Research Center for Agriculture and Forestry, and also the Technical University of Crete, we aspire to use phytoremediation as an effective method to clean mining sites and recover metals. Your target, your orientation is different. You want to create value from decontaminating land and creating biofuels. We have a different perspective. We also want to decontaminate land pollutants, but we want to extract and recover metals from this process. Of course, as I told you earlier, we are at the beginning of this journey, and this is a task that is scheduled to begin next year. So there's not much to report and share with you today, unfortunately. About the expected impact of Extract, well, we would like to develop innovative technologies for the extraction of raw materials in the European Union, improve responsible supply of raw materials to Europe in line with the EU principles for sustainable raw materials. Also, to show the potential to reduce substantially the greenhouse gases emissions, and to promote the utilization of the United Nations Framework Classification for Resources, and also the United Nations Resource Management System in the raw material sector. Finally, we'd like to accelerate development of EU domestic raw materials exploration projects, integrating innovative technologies. This is the Extract implementation plan timeline. We are at the left of this timeline at the moment, at the very left. And this is the Extract website and the social accounts. I encourage you to visit our site regularly in order to read our updates and progress. And I believe it would be great if we could find ways to collaborate and develop synergies between our projects. Once again, thank you very much your invitation and for your attention in this presentation.
Thank you very much, Thanasis, for this very interesting presentation. So any questions from the audience, maybe? Indeed, I think that there are good synergies between the work that you have been doing and our project. So Thanos is the coordinator of CERESiS, Thanasis.
Thank you both for very interesting presentations. I just have a quick question for Thanasis Mavrikos.
Yes.
Have you already identified which plants you are going to use for phytoremediation in your case, in Lavrio?
Yes. At the moment, we are at the stage where our partners have visited the place. We have sent some samples from the soils, and they also have taken samples from the plants that are already existing and growing in the area. And they are performing their laboratory experiments and analysis to identify the possible candidates. So I don't have any results at the moment, but we are in this exact process at the time.
Do you know if you are focusing on phyto-extracting plants, or because we did not focus on phyto-extracting plants in our project, but is this the focus or not yet defined?
Yes, we would like to focus in plants that can operate as accumulators to absorb the certain metals and other elements from the soil, so that then we can recover these metals from the plants after we have completed this process.
Thank you very much, Thanasis.
Thank you.
Okay, so since we are, yeah, please.
Also a question. Hello, thank you very much for your presentation. I wish you all the best for your new project. This is Konstantinos Plakas from CERESiS. In follow-up to Thanos' question, what kind of technology are you going to implement to recover the metals after they have been uptaken from the plants? As a downstream process.
I'm not the person to answer this question because it would be better if one of our partners, who are the technology providers, was here. But as to my understanding, they're gonna burn the plants and then somehow recover the elements that were accumulated, that were absorbed by this.
They will implement hydrometallurgical processes and then use. Okay.
I'm a mining engineer. I'm not a tech.
The issue that we are also investigating is also the selective recovery. If you have a mixture of cadmium, lead, arsenic, chromium, how you separate them is very challenging, of course, but it's a matter of.
These are questions to be answered in the future.
So, wish you all the best.
Thank you.
Okay, thank you. Thanks, Thanasis. So then I think that it's time to have coffee. Just have a coffee break for 15 minutes and then return to actually see the overview of CERESiS results. And yeah, good. Thank you all, and thank you for your patience to the online participants. Thank you very much. Κώστα, κάνεις παύση στην κουβέντα ή το κόβεις. Κάνεις παύση και κόβεις. Okay. I can close that.
Okay, good afternoon, everybody. I'm going to present a summary of the CERESiS project phytoremediation outcomes on behalf of all the work package 2 partners, all listed there, from University of Strathclyde, University of Tusha, REA in Ukraine, and UFG in Brazil. So Thanos showed this slide earlier. The purpose of work package 2 in the project logic was to provide material for downstream processing, contaminated biomass from our field trials for the technological conversion work packages, which I'm going to present in a moment, and then information for the decision support system. And the idea, the strategy behind CERESiS was to use perennial grasses for phytostabilization, so not phytoextraction. And why were we doing this? Well, this we saw as a way to maximize the biomass yield, therefore maximize the energy production, hence the income, to minimize the contamination uptake, and therefore minimize downstream issues. And what we believed was this would also give us the maximum contaminant offtake for phytomanagement during beneficial reuse of sites. So I'll explain why that's not a contradiction in the next slide. So this, the forerunner to the CERESiS project, in many ways was the Bioregen Life project, which planted energy crops on 5 brownfield sites in northeast England between 2005 and 2010. And the results here are summarized in 2 slides, pretty complicated ones, but the ones on the left are cumulative yields or biomass yields for up to 3 seasons. The different crops have different cycles, so it's quite complicated. But you can see the triangles at the top, that's reed canary grass, something like 2 orders of magnitude better biomass production than either miscanthus or short rotation coppice willow on these marginal non-agricultural brownfield sites. We were also then looking at phytoextraction, particularly to remove contamination. We looked at the contaminant levels, and these are much higher in the coppice and the lowest in the reed canary grass. You can see the orange is the lowest concentration of zinc, for example, compared to miscanthus and coppice willow. So this is a sort of contradiction. We were getting maximum biomass, but for the minimum uptake of contaminants. However, if you work out the offtake of the contaminant, in other words, the product biomass yield and the contaminant concentration of the biomass, surprisingly, reed canary grass still gives you the most contaminant offtake. So what's not to like about this? I think it's a win-win-win situation because you get maximum economic value and energy, minimum contamination, and that's potentially an economic penalty, or you might argue it's a value if you really believe you're phytoremediating, plus a whole range of non-market benefits, which you might refer to collectively as phytomanagement benefits, environmental and social benefits from reusing these brownfield and contaminated sites, and a variety of ecosystem services. So that's what we set out to try and investigate, whether this worked at larger scale in different geographical areas. And this is a summary, Pam showed us again, of our different trial sites. We went everywhere from northwest Scotland in Knoydart, the top left, to northern Brazil in bottom left corner, to Ukraine, just west of Kiev, and then to Viterbo in Italy. The species we planted, there are actually 6 of them, Phalaris, reed canary grass, and miscanthus in the UK, in Ukraine and Italy, and then in Brazil, equivalent different perennial grass species, so sugarcane and angiocane, and 2 pennisetin species, napier grass and capiasu grass. So we also harvested some existing sites of woody crops, hazel, vine, and willow, and also Arunda donax and Panicum virgatum from Ursaf in Italy. So that was the only switchgrass. We didn't plant switchgrass. We planted reed canary grass. Why is that? Well, switchgrass is a C4 plant, reed canary grass is C3, so it's much more suitable for northern latitudes, Scotland, northern England. And it's particularly difficult to grow miscanthus in those climates too. So a couple of slides on each trial in turn. First of all, the Italian trial sites. This is an area of geogenic arsenic, selenium, and other strange elements, beryllium, vanadium, cobalt, tellurium, and lead. particularly in groundwater. If you look at the bullseye picture of groundwater arsenic contamination on the bottom right, that's transferred into the soil and then through irrigation into crops as well. So there were 3 trial areas and the Unitas farm, 2 for biomass production and 1 for multiple replicated experimental trials. So this is a summary of those 3 areas, the soil arsenic levels in milligrams per kilogram, and then the arsenic in the Rica grass. So generally lower. So we're seeing some arsenic transmission into the biomass, but generally it's lower than in the soil. So we're looking at phyto exclusion probably. Then we come to the Ukrainian trials planted in 2021. They had a miraculous escape from Russian invasion, and we were able to get samples from them further on through the project. These are areas of former agricultural pesticide unloading and unloading and fuel and mineral oil spillages, and there are 2 adjacent areas both planted with Reconarias and miscanthus. So I've particularly looked at antimony because this is a nice one to illustrate this. The antimony levels in the soil were about 160, 170 milligrams per kilogram. The antimony is an organometallic pesticide there. There's also lindane as well. But you can see in the Reconarias, for example, the antimony is 3 orders of magnitude lower concentrations, those are in parts per billion. So again, phyto exclusion is the name of the game. And so again, go to Brazil, 3 chrome and or nickel contaminated sites. The first one, the big picture at the top, is from the tannery waste processing and disposal onto agricultural land, which is a regionally significant issue for chrome tannery effluents. And also the two sites at the bottom are the mine sites for the chromium originally, and then also explosives manufacturing, which have even higher levels of chromium, geogenic chromium, but also nickel associated with them. So these are the 3 sites. The top one, Anakin's, was the only one that had a field trial. The other 2 and Anakin's were used also for pot trials at the UFG labs. So a summary of the results for these 4 species. Quite a complicated table, but you can see the soil concentrations of chromium are significantly higher, 2 to 3 orders of magnitude higher than those in the biomass, which are pretty uniformly low. So again, phyto exclusion. What we did have was a big variation in yield here in the next column. Capiasu grass and the elephant grass were amazing, fantastic yields. 140 tons per hectare. I can only dream of that in the UK for any species. And because of that massive yield, if you work out the product of the contamination in the biomass and the biomass yield, the extracted chromium is highest as well. So nice result there. But again, it's phyto exclusion essentially. But the contaminant offtake, such as it is controlled by the biomass yield. So in other words, it's energy driven as well, which is good because that's what we're going to get paid for, not the value of the phytoremediation, probably. So that's all simple and well and good, but then we come to the UK trials, which upset that picture rather, because we went to the other extreme from the Bioregen project, where we were looking at fairly low contaminant levels in brownfield sites, which were close to agricultural conditions. We went the other extreme, we went to mine sites, historic tailings and spoil areas with percent levels of toxic elements, lead and zinc, cadmium, copper, even 10% in one case. So these are 3 mine sites. There's 2 areas left and centre of the same site in northeast England, and then 1 in Scotland. You can see from the pictures at the bottom, we've used a compost blanket approach to cultivate these. These were previously bare areas of soil, rather like you saw in the last presentations at Labrian. So we used compost. Unfortunately, because it was a small scale trial and we were doing it by hand, we had to use bag compost in plastic bags, but you could do this in bulk material without that. And it was quite straightforward to do. In fact, spread a layer of 50 tons per hectare on the site. And this worked very successfully, not at 50 tons, but maybe 150 tons per hectare as a minimum, to establish Rica gas from seed on the surface of these highly contaminated soils. So we didn't want to cultivate these, we didn't want to disturb the soil to promote distribution and dispersion of those contaminants. So that it worked to grow Recanary grass, and I mentioned phyto management, phytostabilization, where we were able to see that the Recanary grass roots were stabilizing the compost and the soil, the contaminated mine soil below. So the pictures at the bottom were taken after a rainfall event. One of the sites was subject to gullying and sheet wash, and you can see that the fine network of roots and the Recanary grass were stabilizing the soil very nicely. However, when we sampled the biomass, we got high concentrations of the potentially toxic elements, which we weren't really expecting because we were expecting it to be a phyto-excluder. And lo and behold, when we were cutting it by hand, we could actually see when we opened up the stem of the phalaris that we could see this grey dust from the mine site and the soils. So we were suspicious that we had an issue with surface contamination. We were trying not to wash the biomass because we wanted to know what were the contaminant levels in the biomass as harvested, as a implementation, as being the case in implementation. But we also looked at unwashed and washed samples using X-ray computed tomography. You can see straight away that we've got high electron density or X-ray density patches here of dust at the culm where the leaf joins the stem. And they appear to be cleaner in the wash samples. However, when we looked in a bit more detail, we saw that this area between the stem and the leaf was actually trapping a lot of particles. We could see that these were, in some cases, lead minerals, so clearly contributing to the contamination loading of the species. And we tried to develop an effective washing process in collaboration with a chemistry PhD student who was looking at the for indoor plants, and their optimum washing method we used, which was repeated serial washing with 1 molar HCl and then between 80 laboratory detergents. So we can't leave a more aggressive wash than that. It's concentrated strong acid and then a high-grade detergent used for cleaning lab apparatus in 2 different intensive washes. And even so, we still couldn't remove all the contamination particles around this join between the leaf and the stem. So from this, we extrapolate that many reports in the literature may have overestimated the actual plant uptake of contaminants because they've overlooked this residual contamination during washing. Many papers don't say how plants were washed, or they just say material was washed thoroughly, which means nothing, or they wash in water for a few minutes, which clearly isn't as effective as strong acid and strong lab detergent. So we think this is a general problem with the existing literature now. So we've tried to think of a way of working out what is the split of contaminants between the biomass inside the plant that's been actually physically or sort of biochemically taken up by the plant and what is physically on the surface of it, mechanical cross-contamination, if you like. And the only thing we could think of, we couldn't think of a way of doing it with leaching, but we used the fact that the dried biomass is hydrophobic. So we could do a washing experiment and then separate off float and sink material. So the washed biomass is still sufficiently hydrophobic to float and can be scooped off, and then the washings can be settled. So you can see these are 2 samples from the 2 mine sites I showed you earlier with lower concentrations of lead in the floated material, the washed material, and higher in the settled. So clearly we can start to separate out the amount of contamination and work out how significant the cross-contamination is. And this actually is an SEM picture of a wash plant. You can see there's a grain of soil really stuck in the biomass there. So the plant looks like the plant has actually grown around it. So this is a real problem for all phytoremediation studies where you're growing energy crops and contaminated land. They are going to be contaminated. That's maybe the purpose, but you're going to have real problems trying to valorize that material. So coming to the final UK site, the most contaminated one. This is in southwest Scotland. This area had something like 10% combined metals, principally lead and zinc, but also cadmium, copper, and mercury, and some arsenic as well, actually. And we were getting in the unwashed biomass from the first and second years establishment on this site. I mean, a really challenging site. There was nothing growing there before. It's also an upland site, and it's been there for 100 years or something. And very small growth of Reconary gas for quite a good establishment. So we're quite pleased with that on our compost blanket. But we're getting something like 1% total metals in the first year dry biomass, slightly less in the second year. But this is unwashed biomass, I know, but even so, this is probably the highest levels reported in an energy crop species, we think. And I said that provocatively about a month ago in Athens, and nobody emailed me to say, oh, I've got something with higher levels in. So as far as I know, but I'd like to see something grown at Lavrion to see what that comes up with. So to summarise the UK sites and to look at what's happening in a bit more detail with this in terms of the offtake and how that relates to the very highly contaminated biomass. These are the yields for all the UK sites. So we've got high yield in the second year, obviously, as this is first year's establishment year for Valaris. This site here is the mine site with the highest contamination level. So it's not the lowest biomass yield, but it's an intermediate one for the mine sites. And there were some even more challenging brownfield sites with less contaminated, but still more difficult to cultivate. So looking at the contamination for the different elements. So green again is this second site with the highest levels. You can see that the lead's pretty consistent, but zinc increases in the second year. In the yellow site there, zinc also increases, but there are lead, for example, in the yellow site decreases in the second year. So there's inconsistent results. There's no obvious pattern of increasing or decreasing biomass contamination levels between year 1 and year 2 that we can see. In terms of the offtake, the highest offtake is still this site with the highest levels of lead and other metals. So this isn't the highest biomass now. So this is different from the other results in the other 3 countries. So this is essentially driven by the contamination load. And interesting, going back to the other extreme, to what I started with the bioregen project and the very low level contamination on these brownfield sites. If you look at the contamination levels there, they're much, much lower, of course, 2 orders of magnitude lower, 1 or 2. But the actual removal rate in terms of grams per hectare per annum is roughly about the same. So, and still very small. We're talking about hundreds of grams per hectare per annum. So although we got quite excited about the high levels of contaminants, because the biomass yield is reduced on these, you still can't win. You're still limited to the same amount of offtake. So in conclusions, the contaminant offtake is controlled by soil contamination in the highly contaminated sites, not by biomass production. But this also limits the yield. So it's controlled that way, and at least partly sufficient, not actually taken up by the plant. So it's not extracted from the soil. So that's important because that means it's not actually phytoremediation. It's not actually changing that soil. It's not improving that soil. It's just moving some of it somewhere else. So it's not phytoremediation. So we have to be careful about what we call it. You could call it phytoremoval maybe, and you invent a new word, or you could just accept that it has wider benefits. So why not just call it phytomanagement? But please don't call it phytoextraction. So what do we know as the CERESiS project ends? We've confirmed that Valaris is a viable high biomass, low contaminant uptake energy crop species in England, and we already knew it was in England and Scotland, but also now we've grown it in Italy for the first time and Ukraine, but we found that it may need irrigation to establish even the west coast of Scotland last year with droughts and the climate change, and that was the case certainly in both Italy and Ukraine. But once it was established, then it was okay, it was good to go. Generally, it's a low uptake phytoexcluder, hence low levels of arsenic, antimony, and chromium in the geogenic and anthropogenic contaminated soils in Italy and Ukraine. And likewise for Pennisetum, our best crop in Brazil that had low uptake of chromium and nickel. But we observed these very high levels of cross-contamination from surface dust, which we think is from wind blow or rain splatter on these very highly contaminated and vegetated mine sites. So if that's the case, then as you manage them and grow something on them, then that mobility of the soil will be reduced. So this might actually reduce in future. If we had 5 or maybe 10 years to study these sites that we've established in CERESiS, we'd hope to see that through vegetation establishment then and covering the bare soil, then the actual contaminant uptake from this process would reduce over time. So in conclusion, the biomass contamination and yield reflects the soil contaminants and levels. That's maybe not quite so surprising, but it's not the way we expected it to work at the beginning of the project. And what we've seen is that the contaminated biomass is going to be extremely challenging to valorize by washing, even when it's contaminated by surface particulates, because these just don't wash off. They're very well stuck. So in conclusion, it's this approach to growing energy crops on contaminated land is a good one for low indirect land use change biomass on marginal lands for sustainable biofuels in Red 2 division. And it's good for phytomanagement, but not phytoremediation, please. Thank you.
Any question from the audience or from the online participants for Richard Lord? I don't know if there is any hand raised from our online participants. Let's check. No, one let's see. No. I see one question by Mr. Altner, if I'm correct.
Yes, can you hear me?
Yeah.
Yes, thank you very much, Richard, for this very impressive presentation. I really like this investigation, what you and your team have done on this lead, let's say, issue. I think this is a really a great thing. And I was wondering, I mean, you figured out this with lead, but did you also see similar, let's say, behavior with other metals as well?
So did we see the similar behavior with other elements? So the thing about lead is because of its density, or the density of lead minerals, in this case lead carbonate, but it could we were able to observe and identify the lead-bearing grains on the surface. So we knew for sure we had high X-ray density particles, which, I mean, they look like soil. You can see them. They look like mined soil actually, because they're very fine grained. So that's what you get in grind up ore material. But the good thing about lead was because of its high X-ray density, we're actually able to identify it from the spectrum. So without a point analysis. So that would be the next step to confirm that we've also got other ore minerals there as well. So I don't know. It's a short answer. In the past, we found, well, if you look at the BioRegen results, we got more uptake of zinc, and that's typical in all biomasses. Zinc, copper, maybe cadmium, and nickel. So are generally taken up by plants more readily than lead. But we think that this is a general problem. So if the soil from the mine site on the plant, it will have all of the difference from the mine.
Okay, thank you very much.
Any other question? If not, then we can kindly invite Dr. Boukis to present the next presentation. One moment, close this one.
Starts. Good afternoon again to anybody. I will give you a presentation only on the supercritical water gasification process itself, and then the gas stream gas upgrading. It will be presented to you to Professor Jean-Michel Lavoie. We are lucky that he is with us. Now to the ECWG process chain. Subcritical water gasification is a technology in which the biomass will be gasified, and the main product is a gas which is very clean compared to conventional gasification. It doesn't contain dust, contain only low amount of sulfur, but nevertheless, in order to perform downstream catalytic reaction, someone has to remove also the last small amounts of sulfur from the gas. This will be presented you later. Then a lot of hydrogen you will need later is trapped in form of hydrocarbons. Thus, it is necessary to gain this hydrogen by reforming reactions. Then it follows the Fischer-Tropsch synthesis. The second mass stream leaving the process is a brine, which will contain almost all the contaminants, especially the heavy metals. The process of supercritical water gasification is a simple process in which biomass will be diluted with water to form a slurry, will be pumped continuously to a system of heat exchanger, salt separation system, and the reactor. The reactor will be operated at high temperatures, about 650 centigrade, and high pressure. We used 280 bar, pressures between, let's say, 250 and 350 bar can be realized. The product gas consists of hydrogen, but with a certain amount of hydrocarbons and CO2. There will be, as I said, a salt concentrate containing ideally all the metals of the salts contained in the biomass, and wastewater, which, as you will see, can be recycled. The right side, you see two photographs. The first is the lab-scale plant we used for the experiments in the framework of CERESiS, and on the far right, only the reactor of our pilot plant with acronym VERENA. This plant has a capacity of 100 kilogram wet biomass per hour. The benefits of this technology are that decentralized applications are feasible, various biomasses are usable as feedstock. As I said, product gas is rich in hydrogen and methane. The separation of inorganic contaminants within the process is possible without additional spend of energy, and the organic contaminants will be decomposed. The first experiments show us that we could reach only low gasification efficiencies. Some carbon still contained in the effluent. Salt separation needed to be improved, and also some coke has been formed in the reactors. In the progress of the CERESiS project, we performed over 100 experiments. This enormous amount of work enabled us to reach continuous operation over 100 hours to increase the carbon efficiency at about 90% and to minimize solid deposits.
On the left hand, you see typical measurements of the gas composition over the time. In the middle, a typical feed slurry, and on the lower right, some photographs of the effluent, which, as I said, will be recycled. The recycling of process effluent does not only minimize the freshwater usage, but also improves the economics of the process, because the treatment of the wastewater would be expensive else. No significant difference in the gasification of different CERESiS biomasses regarding carbon efficiency of or gas composition have been measured. You see the results on the left. The process effluent is free of heavy metals, which is a pre-requirement if someone likes to recycle this water. And the heavy metals, as you can see on the diagrams on the right, can be found in the salt concentrate. We have also identified important process parameters which lead to salt deposition. At this place, I would like to thank Julian Ducci, a PhD student working for the development of this process in the framework of CERESiS, for his enormous work. And now I would like to ask Professor Jean-Michel Lavoie to present you the results of the University of Sherbrooke, beginning with the time.
Okay, guys, again, nice dinner yesterday, by the way. We had fun, and I enjoyed the dancing, although I didn't dance, which is why you still also enjoy the dancing, because if I was to dance, you may not have enjoyed it as much. So we did two things on the CERESiS project, and I will tell you why it was useful for CERESiS, and I will tell you why it's useful towards where we're heading with those different technology, because both of the technology will be scaled up, but not exactly in the same context as we did here in CERESiS. So the idea was to take the gas that was produced by our colleagues and eventually reform this gas in order to make it suitable for Fischer-Tropsch synthesis. The gas that was produced from a supercritical water gasification was not exactly the best gas to be used for synthesis for the Fischer-Tropsch, because something was missing, like direly in there. It was carbon monoxide. Basically, that practically no carbon monoxide. So we had to produce some carbon monoxide. The good thing about the gas, although, it was that it has a lot of hydrogen and a lot of methane as well. So our past experience in the field of reforming, because we have been working in reforming for, I would say, 10 years now, and we have been doing quite a lot of dry reforming. Dry reforming is a process by which you will react methane with carbon dioxide in order to produce a syngas. So basically, the gas that we had was like something that we could use for dry reforming combined with a lot of hydrogen, which is downstream something really cool if you want to do Fischer-Tropsch, because usually you end up being short of hydrogen when you're doing Fischer-Tropsch with something that comes from biomass. Now, the other challenge that we had is that we could not easily import the gas that was produced in Germany, because it would have been really complicated and expensive to transfer gas from one side of the ocean to the other. So we use standard gas in order to mimic the gas composition. It was not exactly the same gas, because we assumed that most of the alkanes were not like as diverse as what they had from the supercritical water gasification. We assumed that the alkanes were essentially methane or methane comparable. So we used this fixed bed reactor that you see on the right-hand side. The fixed bed reactor is something like really classical. The thing that I didn't mention is that our technology, we developed a lot of technology and patents around this, and we usually electrify the catalytic bed in order to do the reforming. And usually we target gas that is not as clean as what our colleagues were producing in Germany. And the idea behind this reforming is really to target primary syngas, which will be way more dirty than what we got from Germany. So the other surprise that we got from this we were a little bit aware of this, but we had this surprise because we were using an iron catalyst. And this is really funny because we started working with this catalyst. It's like basically steel wool that we're buying from the hardware store, like literally steel wool without any treatment that we were buying from the hardware store. And we used this for dry reforming for a decade now. It was really efficient. So and it's tricky because the company that was producing the steel wool went bankrupt. So we went and tried other type of steel wool. It was not as good. So then they put something that's special in the steel wool, I guess. In any case, we had to modify this, and you understand why we were going to different things in there, because from like the outside point of view, you don't understand why we went through this, but this is linked to other things that we're trying to do. So what happened is that we used the steel wool as usual, or the iron catalyst, inside of our Inconel reactor, and things were going great. Is like we're using the gas that is like we were mimicking the gas that came from the Germans and the German team, and it went well, and it was always going well. And this is always worrying when you're working in engineering. So things are supposed to go bad, right? So we start doing the reforming, and progressively we reduced the amount of catalyst, and it was still working. So at one point we removed the catalyst, and it was still working. So first of all, we thought of magic, but unfortunately, magic to this point doesn't exist. So we found out that the Inconel was really reactive in the reaction, and the reactor itself was really doing the job for us. So we didn't need to electrify this, and it was really a simple task up to a certain point to convert this gas. And eventually, if we wanted to go, like, if we want to weaponize this to be a better process, we would use Inconel fixed bed catalyst. I'm pretty sure things will go really smoothly for the conversion of such a syngas. However, this will go into industrial process. So in the nearby future, we're going to be using those kinds of reforming technology on primary syngas. So now what Claudia, the student that worked on this, is doing is really, she's really working on primary syngas coming from really dirty gasification, like classical gasification, thermal, not supercritical, and as dirty as possible, just to be sure that we're able to reform primary syngas for the technology that we're going to be demonstrating eventually in a couple of months. Now, the other objective of what we're doing is use this syngas in order to produce alkane through the Fischer-Tropsch process. So remember I said that the steel wool was not available anymore because steel wool and the iron-based system was something that we were targeting in order to do the Fischer-Tropsch catalyst. So iron was also our concern in there, but the steel wool was not available. So we said, how can we do a catalyst for a fixed bed? It will be iron-based that will allow us to do Fischer-Tropsch synthesis. So this is why we started doing like sintering of iron powder and combining with different structure like copper and potassium. This is what JIRA did. So we did Fischer-Tropsch synthesis, but looking into different other structure of catalysts and eventually trying to print those catalysts in order to optimize heat and mass transfer in those systems, in order as well eventually to be able to do Fischer-Tropsch synthesis at smaller scale, because usually economy of scale is really important for those technology. And we think that we're going to be able, by printing catalysts, eventually metallic catalysts, to go around the fact that we usually need a larger scale in order to make this commercial. So these catalysts, now we did, like you saw the picture previously, it worked well, but it was kind of tricky because we needed to print with plastic, then mix this with like metallic and iron powder, and then sinter this in order to make the catalyst that we use. We have two like plastic 3D printers at the lab, so we didn't go further than that because metallic printer is $150,000 Canadian. So we didn't want to invest in this before we know for sure that this would be useful for where we were heading. And the results speak from themselves. So JIRA was able to do something which is not perfect. You see there, like we babble something interesting in 3D, but it still worked. And it proved the fact that we're able to control the porosity of the catalyst and eventually print something that will allow optimal heat and mass transfer. And this as well will be scaled up for the reforming technology, the printing, I mean, and eventually also for Fischer-Tropsch synthesis. So in this, we also try using potassium and copper. To be completely honest with you, eventually I want to print those metal as well in the catalyst to be able to make it work. So the good thing as well was that we tested this catalyst for a long period. We were able to operate for 100 hours, and we stopped at 100 hour, but the catalyst was maintained in there, which means that we opened the gate towards something that could be eventually a full field of research. And I'm progressively transforming this in a whole field of research, how to print and optimize those catalysts in order to do better catalysts and eventually print this and swing this directly in the reactor. And I think my colleague will give you the conclusions.
Thank you very much for the fantastic presentation. Now to the conclusions. As you heard, both technologies I present you today made a very big step ahead, and it is suitable for CERESiS use cases, but also for other applications. Long-time operation was possible. At this time, I'd like to say that 100-hour operation succeeded as for the first time in the 25 years I'm working with supercritical water gasification. And also high conversions were achieved for both the processes. As you have heard, physical integration was not possible, but I'm sure it is not a problem. And the process chain is valuable. We start with contaminated biomass and we end with high quality fuels. Thank you very much for your attention.
A question from the audience? Or should check also the online participants, there might be a question. No. Any question also from the online participants? If not, then Thanos to move to the next presentation. There is one question by Mark.
No, it was. Okay, thank you. So the next presentation is from Paola Giudiciani on the fast pyrolysis process.
Good
Paola,
afternoon, everyone. Can you hear me?
Yes, we can hear you. Can try to share your screen too.
Yes.
At the bottom, there's a share button.
Can you see my screen?
Yes.
Okay, I'm ready. Okay. Good afternoon, everyone. In this very short.
We
Yes.
see the presentation link. We don't see your presentation. We see ourselves.
Okay.
The online participants. So you try to share different screen or different.
Let me try again. Now, can you see the presentation?
We can see it. Yes.
It's okay.
It's fine. Yeah, you can start.
Okay.
Thank you.
Okay. So yeah, in this short presentation, I will show you the main results that we have obtained during these 4 years regarding the pyrolysis pathway in CERESiS. In this pathway, we propose to use pyrolysis as a treatment for the contaminated biomass, and we investigated several stages of this pathway, from the pretreatment, the production of the oil, the post-treatment of the oil through microfiltration in collaboration with CERT, and also the combustion of the pyrolysis gases to exploit their energetic content to sustain the process. We also assessed the possibility of using biochar for other applications. I will focus mainly on the pyrolysis today, pyrolysis and to the combustion of pyrolysis gases. Okay, if we look at the literature, here I reported a diagram from a paper, a review paper of some years ago of Colomba Di Blasi, that is a milestone in the history of pyrolysis. We can see that to obtain high liquid yield, there is no way we have to work under fast pyrolysis conditions. And this means that we have to operate it, with fast heating rate at moderate temperature and with short vapor and also solid residence time. But in our case, in the case of CERESiS, we have a complication because we have contaminants, so we have to handle this problem. And what we tried to do behind the state of art was to understand how we can adjust the main variables of pyrolysis project, that are heating rate, temperature, solid and vapor residence time, to find a compromise between high biooil yield and a clean biofuel. Let me say already now, from now, that we cannot obtain a completely clean biofuel. We are not able to retain all the contaminants in soil, but our goal is to minimize as much as possible the displacement of these contaminants from the solid to the liquid, also because we investigated in this project also the post-treatment of the oil to reduce even further the concentration of contaminants. And an important point in this study was also to assess the possibility of exploiting the energetical content of the pyrolysis gas. That is a gas that is very challenging because its calorific value, we will see, is very, very low, and it's not easy to obtain stable combustion conditions of this type of fuel. Let's start from the heating rate. The most proper technology for reaching fast pyrolysis, high heating rate, is typically fluidized bed. But again, in the case of CERESiS, we have to take into account the presence of contaminants. So fluidized bed does not represent, in this case, the most appropriate solution. Why? First of all, because of the heating rate. It is true that a high heating rate means high bioil yield, but we know from the scarce literature that is present on this topic that high heating rate are also conductive to the devolatilization of metals. That means to the displacement of heavy metals from biomass to liquid. So we decided to work to operate at the borderline between intermediate and fast pyrolysis, just to find the compromise I explained you before. There are also other points that are not good for contaminated biomass, since fluidized bed requires a high flow rate of carrier gas. That means, in our case, to favor the entrainment of fines during the process. And we know that in this case, fines are contaminated by heavy metals, solid fines. And also the presence of high flow rate of carrier gas produces a high dilution of the pyrolysis gas. So this means that the exploitation of the energy content of this gas becomes even more challenging. So we decided to use another type of technology, that is the screw reactor. That is a well-known technology, very flexible with respect to the particle size and composition. It allows a good control of the residence time and temperature, and also of the particle entrainment. And also in this type of reaction, a good mixing control can be obtained. This is the scheme of our reactor. There is the pyrolysis part on left and the condensation unit on the right. And this is a sketch of picture of the plant that is available here at CNR. And the plant can be operated with a maximum feeding rate of 2 kilograms per hour at a maximum temperature of 600 Celsius degree, and a maximum solid residence time of about 20 minutes. What we did in this reactor, a very wide experimental campaign that was aimed to understand how we can adjust pyrolysis temperature, carrier gas flow rate, and solid residence time to minimize, to have a good oil in terms of quality and of yield, and also to minimize the displacement of the contaminants from the biomass to the solid, to the liquid, sorry. Then after this experimental campaign, we tested several biomasses to assess the performance of this reactor. Let's go to the first results. Here I reported the yield and the characteristic of the bio-oil as function of the pyrolysis temperature. We can see that to maximize liquid yield, pyrolysis should be conducted at about 500 Celsius degree, but to increase the liquid quality, I mean to reduce the water content of the oil, the temperature should be raised to 600 Celsius degree. And what happens to the contaminant? In this case, contaminant is zinc. Zinc displacement increases greatly from 550 Celsius degree up to 600 Celsius degree. So how can we select the optimal temperature? We have to prefer high quality of the yield, or we have to prefer low contamination. It depends on the initial contamination of the biomass. In the case of CERESiS biomass, the contamination was not very high, so was not so critical. So we decided to push temperature and to operate at 600 Celsius degree. Also because we have in mind the post-treatment of the liquid yield, aimed to reduce the solid content. Here I reported liquid yield and composition at different solid residence time inside the reactor. We can see that the yield of the liquid remain almost unchanged, as well as its water content, but the solid and contaminant content decrease as the solid residence time increase. What happens when we decrease solid residence times? We increase the rotation speed of the screw, and this favors the attrition between solid particles and produces more fines that are transported into the liquid. So it is better to work with low rotation speed of the screw. That means at high solid residence time. What happens when we change the nitrogen flow rate? If we look at the bio-oil yield, we can see that low nitrogen flow rate negatively affects the liquid yield. Why? Because we reduce the heat transfer both in the pyrolysis reactor and the condensation and in the condensation unit. Then liquid yields increases, and at the same time water content decreases. What happens to the contamination? We can see that even though at higher nitrogen flow rate, the solid content increases, the contamination, the displacement of the contaminant to the liquid does not change. So this suggests that in these conditions, in condition test in our reactor, the main mechanism that displays the contaminant from the solid to the liquid is devolatilization rather than elutriation. Here I just want to give an idea of the performance of the reactor. We can see that the liquid yield on dry basis, the average liquid yield is about 27%, but the liquid contains high amount of water. So the yield of the organics is about 12%, but it is worth to be noted that this is the liquid that we collected, and the mass balance in our system closed at about 88 to 95%. So this means that a critical step in the stage in the pyrolysis process is the condensation. And by improving the condensation system, we can obtain even higher liquid yield, mainly organics yield. What we observed, but it is just a confirmation because this is known in the literature, that ash is the presence of ash in the biomass is detrimental for the liquid yield. In fact, we observed a very low liquid yield for sugarcane that has a very high ash content, more than 10%. And we can see from the table below that the solid content is the standard deviation is very high. So this means that the solid content is very variable, and it depends on the quality of pellets, because we use pellets to feed the reactor. And the quality of the pellet is related to the composition, initial composition of the biomass, especially to the presence of lignin and of ash. But let's look to the contamination. If we look at the diagram on the left, we can see that the concentration on the main contaminants that are zinc, chromium, and nickel is very variable, because it depends on the initial level of contamination of the biomass. But if we look at the diagram on the right, where I reported the displacement of each contaminants calculated as amount of contaminant in the liquid divided by the amount of the contaminant in biomass, we can see that for the same contaminant, the displacement is only slightly dependent on the initial concentration in the biomass. But what we can see is that is very highly dependent on the type of contaminants. More specifically, in this case, we can see that chromium exhibits a different behavior with respect to zinc and nickel, and is characterized by lower displacement in the liquid yield than zinc and nickel. So I want just to give an idea of what we, on the work that we did on the combustion of the pyrolysis gas. This is a typical, in these two diagrams, I reported the typical concentration of the pyrolysis gas that we obtained with biomass tested, and the concentration is not very variable, and also the calorific value is always values around 11 megajoule per kilograms. So this gas is quite challenging as fuel. But what we try to do, we decided to use a peculiar type of combustion regime that is called mycombustion, and is characterized by high diluted fuel loads with a temperature, an inlet temperature higher than the ignition temperature of the fuel, and with moderate temperature increase inside the reaction chamber. In the diagram, this regime is represented in the bottom right part of the diagram. And in this project, we achieved this regime, recirculating the hot exhausted gases towards the fresh reactants using a cyclonic flow burner that is in this picture. This burner has been tested with this fuel in a wide range of operating conditions. We selected different types of pyrolysis gases to span the calorific value from low to higher values. And what we have observed that a stable combustion can be achieved even for pyrolysis gas with very, very low calorific values. And also the emissions that I reported here as CO and NOx are very low under the limits, the regulatory limits for the traditional burners. So in the end, we used the screw reactor as technology to treat heavy metal contaminated biomass. We have seen that most critical parameters affecting the bio-oil yield and quality in terms of water content are temperature and carrier gas flow rate, whereas the temperature mainly controls bio-oil contamination. So the choice of the optimal temperature should be done taking into account the type of contamination and the initial contaminant content in the biomass. Finally, we have demonstrated that the calorific value of the pyrolysis gas Even if it is low, it can be efficiently exploited using this peculiar type of combustion that is called mild combustion. Thank you for your attention.
So, any questions from the audience? Both online and in person?
If there are no questions, we can proceed with the presentation from SERF on the separation and decontamination technologies of
Costa centimeters together. I assume you can all see my screen from those attending from distance. So, good afternoon, everybody. On behalf of my colleague, Dr. Dimitris Koutsonikolas, and of course of all colleagues from the two laboratories participating in CERESiS project, namely Artemis and NRRE laboratories of the Chemical Process and Energy Resource Institute. First of all, I would like to express our pleasure and gratitude to being part of such a great consortium. Really, we achieved a lot by working together, reaching major milestones and achievements. Thanks, although Thanos is not here, to the excellent coordination of Professor Athanasios Redizelas and of course of his colleagues from the National Technical University of Athens, Dimitris Katsorinis and Dimitris Yiannopoulos. Thanks to you guys, we really achieved all the technical and other scientific objectives set from the very early beginning of the project, keeping the train on track regardless the COVID pandemic and this Russian invasion in our Ukrainian, affecting our Ukrainian partner. Of course, you all understood from the previous presentations that the heart of CERESiS projects deals with land decontamination by developing phytoremediation, phytoremoval, phytomanagement. I don't know, Richard, how I should say these techniques. Why to have the necessary biomass in order to produce non-ILUC, I would say, biofuels. But the two laboratories here at CERT had a major role also in downstream processing, how to upgrade or to decontaminate the various gaseous and liquid outputs produced by the two thermochemical processes shown previously by Dr. Boukis and Dr. Paola Titiani. As far as the SCWG process, colleagues from the Artemis laboratory carry out a very systematic research on desulfurizing the gaseous product of the SCD process, reaching a TRL5, I would say, on the developed membrane gas adsorption process. And we at NRRE laboratory carry out a systematic, again, investigation to develop and optimize, I would say, a rather novel electrochemical-based processes that combines the electrocoagulation flotation process for removing inorganic contaminants, such as heavy metals, with the electrochemical oxidation process for removing the organic contaminants included, where is the brine effluent produced by the SCWG process. In the case of the fast pyrolysis process, as we heard from Paola previously, the bio-oil potentially can contain charred heavy metal laden particles that are necessarily to be removed in order to upgrade the final product, the bio-oil. And for that, we investigate for the first time ceramic nitro filtration with the aim to remove charred particles of size lesser than 1 micrometer. So, starting with the electrochemical decontamination of the SCG saline wastewater, as you can see, the target was to develop a hybrid
process for effective removal of both organics and heavy metal. On the right, you can see the principle of electrocoagulation, electrochemical oxidations. And for those who are not aware of the two processes, from one hand, we want to produce in situ all the necessary chemicals, in our case, iron oxides, that are necessary for interacting with the heavy metals and removing them in form of precipitates. And from the other hand, we are based again on very special electrodes that can in situ produce strong oxidants, in our case hydroxy radicals, that can decompose, mineralize the organic contaminants. So the challenge was to effectively remove these pollutants, also with fast kinetics to consume lesser energy if possible. We understood with no use of chemicals because all chemicals are produced on site, and to reduce, of course, the energy consumption. And what was our plan? First, to design here at CERT. We will have the opportunity during the lab visit to see the novel electrochemical coagulation flotation lab pilot unit we designed and constructed in-house here at CERT. To upgrade also a lab-scale chemical oxidation unit for all these anodic oxidation studies, to validate the two processes in the laboratory environment using simulated saline wastewater that mimic the supercritical water classification brine effluent, and to validate the hybrid process in relevant environment using, in this case, real saline wastewater sent by our colleagues from the KIT in Germany. In this slide, you can see on the left the electrocoagulation flotation laboratory pilot setup, and on the right you can see the electrooxidation base scale setup. Up you can see the different electrodes applied for the electrocoagulation. We tested 3 different electrodes as sacrifice anodes: iron, aluminium, and stainless steel. While in the case of the electrooxidation, we had a very good knowledge, and we counted on boron of diamond electrodes for carry out the anodic oxidation test using as cathode a porous carbon material, a gas diffusion electrode that promotes also the in situ production of hydrogen peroxide. For the feed solutions, to mimic the SEWG, we use salts mainly of potassium because, according to KIT, the major building salt element is potassium, and lead as a model heavy metal. In the case of the electrochemical oxidation studies, we use phenol as model organic compound, and again, potassium salts in ionized water. And you can see down there the characteristics of the real brine shipped and collected received from KTI. Here only one slide concerning the results. From the left-hand side, you can see these very nice graphs. These are produced by design expert software because we wanted to optimize the process by investigating the effect of 3 main process parameters. What is this? The electrolysis time, of course, the current density, and the pH. And also, with the aid of the response surface methodology, we found also some correlation models relating the lead removal and the energy consumption. And what did we observe? That with very low electrolysis time of about 9 minutes and with low current density, we can achieve almost 100% of the lead contained in this simulated wastewater. In the case of the electrochemical oxidation, we try to optimize the process by using phenol as model compound, at different current density and flow rates that affect the hydraulic residence time. And what did we observe? Again, with low current densities and high flow rates, because they promote the removal of the gases that are produced in situ due to the mineralization of the phenol, very high removals of phenol, very high mineralization rates indicated by the TOC values reaching up to 75%, with rather moderate energy consumption close to 80 to 90 kilowatt hours per cubic meter of brine treated. And what is studied for the first time in literature is to combine both processes in a single setup to simultaneously remove lead and phenol, because by this way we reduce the total energy consumption, as you may understood, and surprisingly we observed very, very high removals of both the lead as expected, and together phenol and TOC at a very, I would say, low energy consumption. So the main conclusions out of this research carried out concerning the brine SCWG wastewater is that lead ions can be effectively removed using especially iron sacrificed electrodes, because the two other electrodes, aluminum and stainless steel, do not present the same results. Very high mineralization, complete removal of phenol achieved by the BDD anodic oxidation of both simulated SCW brines and the real brines. And we have seen also that the combination potentially is also maybe a matter of patent, I don't know, in a single setup with two pairs of metal electrodes proved to be very efficient for the combined removal of phenol, POC, lead, as well as nickel ions under optimum operating conditions. And now I give the floor to my colleague Dimitris to continue.
Hello all, also from my side. I will try to give you a very quick overview of our activities in the CERESiS project regarding the development of an MGA process for supercritical water gasification gaseous product upgrade. And first of all, starting from what is this process, MGA stands for membrane gas absorption, which is a hybrid process that combines the advantages of membrane technology with that of conventional absorption processes by using microporous membranes instead of packing material in order to provide the gas-liquid contact area. The process principle, you can see in the graph in the left. We have a microporous membrane and the two flows, a gas phase flow on one side of the membrane and the liquid phase flow on the other side of the membrane. As we use hydrophobic membranes, the pores are gas-filled. So if we keep the liquid pressure slightly above the gas pressure, then we have an immobilized gas-liquid interface formed at the pore's mouth from the liquid side. And this is where the absorption or the reaction takes place. With this way, we can achieve very high and very well-defined surface area compared to packing columns and packing materials. Almost an order of magnitude higher surface areas compared to packed columns. This is a comparison of the two different technologies, the typical conventional packed columns versus the membrane conductors that we used in this project. There are a lot of pros and cons that you can see in the table, but the main advantages of the MGA process mainly comes from two distinct characteristics of the membrane technology, and these are the very high specific surface area. So we create very compact devices in order to run a process, and the other main characteristic of this technology is that the two flows are not mixing each other. So we have not the typical problems that we commonly see in scrubbers and packed columns, such as column flooding or foaming or all this kind of stuff. And this process, the MGA process, has higher performance in lower volume. Some disadvantages mainly deal with the membrane itself, which can be wetted and reduce the performance with time. It's a typical problem, and we have always to have in our mind the membrane stability and the compatibility of the membrane with the different solvents that we would like to use. But the main characteristic of the MGA technology is that is very well fitted for small scale and decentralized applications that, like that we are examining in the frames of CERESiS project. The main operating parameters of this technology are the following. As you can see here, First of all is the feed gas flow per membrane area. It's something similar with the gas residence time in a packed bed reactor. So it affects the process performance. Then, of course, the gas to liquid flow rate ratio that also affect the performance, the solvent type and concentration, which affect the performance of the process, but also it has to be checked also the stability and the compatibility with the membrane and the operation mode, which could be once through or in a recycle mode till solvent saturation. These are only some indicative results created during the project. In the first part of the project, we mainly focused to parameterize the process, to see how the different variables affect the process performance. And here you can see that we examine the effect of gas phase flow rate. The left and the right graph has the same process variable, except the feed gas flow rate, which in the right graph is half of that in the left. As you can see, by reducing the feed gas flow rate, meaning that increasing the residence time, of course, we increase the performance of the membrane. Then we compared the different two different solvents, the ethanolamine and methyl diethanolamine, which have different reaction pathways regarding their reaction with CO2 and H2S. And we can observe that the ethanolamine is better when we would like to have combined CO2 and H2S absorption, but MDA is better when we would like to target on selective H2S absorption. And the liquid flow rate is a controlling parameter which can be used to, let's say, control the level of contaminants removal in the process. In the second part of the project, we focused to test the technology and create the knowledge that we gained before in order to check the stability and the performance of the process at application relevant environment, creating a syngas that has similar composition with that produced in the experiments carried out by KIT. So in the two graphs, we can see that in the selected process condition, which were selected based on the process parameterization results, we have a very stable process which can achieve more than 98% of H2S removal from the treated gas, and at the same time, about 60% of CO2 removal. In the right graph, you can see the effect that I was previously described, the membrane wetting, which after some operation time increases the mass transfer resistance of the process and decrease a bit the performance of the system, but it mainly affects the CO2 absorption. But this is a reversible phenomenon which can be compensated by a periodical membrane drying, or if we, let's say, operate the system at a bit lower gas to liquid flow rate ratio. And these are some key conclusions and key achievements that were achieved during the CERESiS project. And we designed a highly efficient, flexible process in CERESiS project, targeting to deep H2S removal and moderate CO2 removal. Based on the results, MDA and high gas flow rates favor the selective H2S removal, while the ethanolamine and low gas flow rates favor combined H2S and CO2 removal. The process conditions for deep H2S removal and moderate CO2 removal were identified and demonstrated at application relevant environment. And in any case, in all experiments, the viable components of the process, meaning the methane and hydrogen, were 100% recovered in the treated gas. So the overall performance of the process was very good. And with this, I think we completed the presentation regarding the MGA process, and Kostas will continue with the fast pyrolysis.
Very fast, only a few slides concerning the fast pyrolysis process. Again, we stay with membrane filtration process, which our lab, we are proud to have more than 30 years of experience. Again, here we use the ceramic microfiltration membranes, microporous, because membranes, as you understand, are filters that are acting as barriers to remove particles that have a size larger than the pore size of the membranes. In this case, we used ceramic membranes to remove heavy metal laden charged particles included in the produced bio oil. That was our main target and challenge, was to understand also and quantify one major problems that we faced in membrane processes, and that is the membrane fouling when dealing especially with highly viscous liquid streams, such as the emulsion produced during the fast pyrolysis process. And the plan was to design and construct a house, in this time a ceramic membrane microfiltration lab pilot unit, and this took place during the first year of project implementation. Then to test the different membrane modules purchased for this scope by assessing the water permeability at different cross-flow velocities and transmembrane pressure. First, to carry out some preliminary experiments with synthetic mixtures of glycerol, water, and powder activated carbons that emulating the relevant bio-oil properties. And during the last, I would say, year of the project implementation, to carry out tests with real bio-oil samples produced in Italy by STEM's CNR. Here on the left, you can see the microfiltration laboratory pilot setup, especially which is composed of the membrane housing, the pump, the feed tanks, and all the necessary equipment for the control and supervision of the operation of this pilot setup. Has also a PLC for remote control and monitoring, followed by SCADA. On the right, you can see the membranes. We ordered membranes from two companies, one German one, Atec Innovations, and one Chinese one, Wocho Technology. All of them have the same support, alpha aluminum oxide, and different active layers, different oxides, as you can see, different number of channels, either they were mono-channel or multi-channel, and different also filtration pore sizes. And with the collaboration of Artemis also, because these are ceramic membranes. Ceramic are in general hydrophilic. We aim also to hydrophobize these membranes to check whether we, at the same time, while removing charged particles, we can remove also partly water out of the bio-oil. And see, here you can see some indicative results from the microfiltration test. On the left, results concerning the simulation experiments using glycerol, water, other active carbon solutions before hydrophilization, which is with the green dots, and after hydrophilization with the red dots. What was surprising, although yes, we observed some flux decline, the transmembrane pressure was very stable, meaning that the fouling on the membranes was reversible and not affecting the process itself. And also, as you can see from the microscopic analysis in these cases, almost all charged particles were removed and the permeate is clean, while the retained particles in the concentrate form aggregates. In the case of the real bio-oil experiments, again, what we observed with the synthetics was similar with the real bio-oil. The transmembrane pressure was very stable. Only, as I would say, moderate flux decline was observed. But after the cleaning of these respective membranes using the protocol proposed by the manufacturer, again, the flux was recovered and was similar with the first initial conditions. And here also we can see the microscopic analysis of the reference permeate and the concentrate. Again, the total removal of the charged particles included in the sample sent by CNR. So the main conclusions, in the case of the modified membrane, we observed, I would say, a significant decrease of water permeability, about 15 to 20%, with no effect in transmembrane pressure. No fouling was indicated by the transmembrane pressure for profiles. In any case, fouling was reversible after appropriate clinical protocol was followed. And we observed total retention of capital particles in both simulated and real biofuel samples. Of course, teamwork makes the dream work. Without our people in the two laboratories, nothing of this could be possible. And from this point, I would like to thank all my colleagues that are sitting behind. You can see them there. From NRRE Laboratory, Vasilis, you can stand up if you like, who tolerate to manage the fast pyrolysis of bioil, but it was very, very smelly, and that's why all the experiments were conducted outdoors, or else they will kick us out from CERT. Panagiotta Petsi carried out, I don't know if she's here, no? Carrying out all the electrochemical oxidation experiments, Vasilis Hadjir, a former colleague, and of course, Michalis Lekas, the automation engineer. Without him, we could not produce all these nice setups that I showed you previously. And from Artemis team, all these nice guys that we have the pleasure to collaborate this during this 42 months of CERESiS journey. And with that, we conclude, and thank you very much for your attention. I don't know if there is any question in the audience at this level. Online and in person. If not, we can continue.
Thank you, Costa. And we have one final presentation. I know it's a bit late and we're getting hungry, but it's the last presentation of the decision support system demonstration. So I would like to call our colleagues from Intrasoft to introduce us to the first public demonstration of the decision support system, so that people can see how it looks like.
Okay, so thank you very much. There aren't any slides as an introduction. Without further ado, I would just like to give the floor to my colleagues, Christos and Thanos, who will demonstrate live the system for you to see its capabilities and its potential. It has been a very nice journey all these past few months. Thank you very much, and let's hope for all the best.
Okay, hello from my side. Thank you, Professor. Okay. Okay, so here we see the landing page, what we also saw yesterday in the demo, in the video demo. We'll show some steps for the current version and how to use it. So let's start. We see some basic guidelines in order to choose the fields. We have a map here that is pointing to Europe, let's say. And we can start now creating and marking our fields on the map. We can go here and let's start creating some fields. We have two possible options at this point for creating the fields. One is a circular, let's say, marker, and the other one is a marker that is able to do more complex, let's say, shapes in order for the user to mark specifically the field that they want. You can, of course, zoom in and out at, as you see, a very low height in order to mark the field specifically as you want. You can also delete any fields, and very importantly, to update or edit any fields as you see fit, if you have made any mistakes. All the information regarding the fields appear here on the right side, on the right sidebar. We see some generic information regarding the area in square meters, as well as the coordinates which signify the center, let's say, of each field. Also, the user has the ability to export the fields. This means the area, as I said, as well as the coordinates and the distances between each of the fields. And after that, you can press the next step. From here, we should choose the automatic selection of biomass, which under the hood uses, let's say, the ML model that signifies the best biomass. We have here a set of contaminants to choose from. Nevertheless, we can also use the default values if we do not know specific information for this part. We have to use the soil texture, and we can click submit. And now these are the results from the ML model. We see here the 3 biomass types as well as the suitability and the yield. Here, of course, you should choose at least one in order to proceed. Let's choose these 2. We press on, and now we can move on to the optimization input part. What you see here in the placeholders are the default values that are going to be used, unless the user changes them. We can proceed now with the default values for this example. We press submit. This runs the calculation of the optimization model, and now we get back this page. Now this is the result view, the details view. Here you see a set of KPIs for each, and a set also of scenarios, which is a pair of the biomass and the technology, as you see in campus and fast pyrolysis, for example, etc. Now from here, you can press on the header of each column and see detailed results for each specific scenario. As you see, we have different results in this case. From here on, you can see that we have broken down, let's say, in logical, let's say, parts, the results. We see that the revenues cost, conversion cost, transportation, and emissions. We also have visualization next to our tables in order to make it more easier for the user. The visualization, of course, can be changed in order to be either as bar charts or pie charts. Moreover, the user has the ability to download in a CSV format the results and also play around with the density filter and filter the values in the columns of each table. Other than that, we have the map on which the suggested routes, let's say, have been created. As you see here, we have all the possible routes for the 4 fields we have already put on the map, the user has put on the map. And the user also can press on specific icons to see what each icon is, the location, as well as some generic information regarding the capacity, for example, as you see here. And more specifically, if the user wants, can choose a specific route of the ones presented here in order to see only the specific route on the map in order to clarify better the results. Each time the routes are recalculated in order to be presented again to the user. Moreover, we have the ability by pressing on each specific line to see the comparison between each specific scenario. As you see here, we have for miscampus and fast pyrolysis, miscampus supercritical water classification, etc. Now this will be enhanced in the next few days in order to have a breakdown, let's say, stacked bar chart in order to show the results in more detail. But this is the functionality for now. And other than that, we have the multi-criteria assessment. Now here, as you see, we have the KPI significance for all the above KPIs. We also include here some information regarding each KPI. And here we have the weighting factors in general for the environmental KPIs. As you see, we can highlight which are the ones that we care about. The same is for the economic and the social KPIs. Now, by pressing assess, we have the F-score for each specific scenario. As you see, miscampus supercritical water classification, in this case, it gives the highest F-score. By changing the weighting factors, let's say we change this. Of course, the totality changes in order to be 100%. And pressing again assess, you see that we dynamically change the F-score of each case. This goes, of course, for every case of the weighting factors regarding the environmental, economic, or social KPIs. As you see, we see the difference here. And this also can be effective by changing the KPI significance for each specific KPI. As you see here, we have different results. This is the main functionality regarding the result view, let's say, where we have the details of each run. Then in order to run again the example and place new fields or start a new process from the beginning, the user just has to go to the main view and they can restart the process. In order to review the results and revisit them if they need, we have added this functionality where the user can press the user view and seeing the already implemented, let's say, runs that they have executed. If they press again, they will be redirected to the results view and they can see the results and the numbers and the calculations again from scratch. This is all from my side. Thank you.
Thank you, Christos, for the quick overview. It was quicker than expected. Are there any questions? I guess you are hungry. So, are there any questions on the children support system that we showed? It's not yet available publicly online. We still have a few tweaks to make, and in the next few days or perhaps a couple of weeks, it will be available. I think you got an idea of what it looks like and what the aim is. I don't see any questions. I presume this is, we can wrap up and go for lunch. So it's been a very interesting 3.5 years, very productive 3.5 years. We've achieved a lot within this project. Today we showed what has been achieved within CERESiS. We also had very interesting interactions with related projects, either in the same call or adjacent areas, which are all opportunities for collaboration. We have quite a number of online participants, so thank you all for attending. Thank you all for contributing to CERESiS. And let's hope for a continuation of this effort in the future. So thank you very much, everyone.